Hey everyone, my name's Jacob Strickling and welcome to the Year 8 High School Physics course. Now to complete this course you are going to need a work booklet, either on paper or in digital form, and you'll definitely need a Tiny Science Lab physics set which is absolutely loaded up with all sorts of good things, good sort of physics things. And talking about physics, what actually is physics? Well, that's a good question. Physics is about the study of motion, forces, energy, electricity, magnetism, light, that sort of stuff. Very important to understanding how this world and this universe interacts and how it goes all together and how things work basically. So absolutely fundamental. And we are going to be doing a whole bunch of experiments, a whole bunch of investigations in this course. Most of the lessons you'll just be using the equipment from the physics course, but some of the lessons you will need a few little bits of extras. For example, like sticky tape or bits of hose, or what else might you need? A couple of tubes, maybe some A4 paper. So nothing that you really have to go down to the shops and buy. It should be around the house or even at the school, stuff like that. But anyway, I'm very excited for the next 20 or so lessons, and so let's get into it. Welcome to lesson 1 of the Year 8 High School Physics course, Energy Interactions, a summary. So, in this lesson we're just going to define what energy is. We're going to list the 9 forms of energy and give a brief explanation of what they are. And we're going to look at some energy transfers and what an energy transfer is. We're going to look at the first law of thermodynamics of energy, otherwise known as the conservation of energy, and have a quick look at the second law of thermodynamics as well. So, when I was in high school, early high school, year 7, my teacher, Mrs. Rockwell, fine lady, taught me that energy is anything that causes change. A very simple definition, but one that has been perfectly adequate throughout my life as a teacher, engineer, all the science stuff I've done. A great definition. Energy is anything that causes change. So, what are the forms of energy? Well, kinetic energy. Kinetic energy is one of the forms, and kinetic energy is moving energy. Things that are moving have got kinetic energy. Yeah? So there we go. This ball has got kinetic energy when I roll it, but when I stop it, it doesn't have kinetic energy. No kinetic energy, some kinetic energy. What about if I roll 2 balls at the same time and at the same speed? So the steel ball and the rubber ball. Which one do you think has the most kinetic energy? They need to be going at the same speed. Provided they're both going at the same speed, you might say, same. Well, you'd be wrong. It's actually the one with the biggest mass has got the biggest kinetic energy if their speed is the same. Now, I've got a little image here of a spoon on a chain. And if you wiggle the spoon, then you give the chain some kinetic energy. So if you wiggle the spoon, you'll give the chain some kinetic energy. And we're definitely going to be exploring this more later. So that's kinetic energy, the energy of movement. What about sound? All right, well, if we clap our hands together, we can make a bit of sound energy. If we drop, if we drop the steel ball, we make some sound energy. But I've actually got a picture here of a kid blowing into a rubber band an elastic band, and there's 2 paper clips. And those 2 paper clips are there just to create a little tiny gap in the rubber band when you pull it apart. That's the idea of those 2 rubber bands, just to create the smallest gap. Now, my rubber band's a little bit twisted up. You might have a black rubber band there, or you might have a brown one. Actually, you might have a black or a brown one, but they should still be about the same size. And see, there's a tiny gap now between those 2 sides of the rubber band. And I'm going to try and blow into it. Feels funny. Sounds like an old style aeroplane, or even a helicopter. Very interesting vibration, isn't it? Sound is produced by a vibrating object, and sound is a form of energy. And sound is picked up by our ears, converted into signals which our brain interprets as sound. How good is that? Okay, so that's what sound is. Sound is, it's produced by a vibrating object. What's the next one? Heat. Well, for heat, you're going to need this little piece of PVC tube, and you're going to rub it firmly onto some magic carpet. Well, just carpet will do. So let me go down here, rubbing the PVC tube onto the carpet, and then I'm going to put it just on the back of my hand. Ooh, it's warmed up. Okay, it's warmed up. So when you rub it, it causes the particles to start moving faster via the friction, and when those particles are moving faster, we call that heat, yeah? So if you rub your hands together, you can actually feel them warming up. Can you feel your hands warming up when you rub them together? Push and rub the hands, and then you can, that actually feels really good. Yeah, that is heat. And heat is the kinetic or the moving energy of particles. All right, what about light? Well, I've got a mobile phone here, and mobile phone is it's got a light, and light, very, very interesting phenomenon, light. Like, what actually is light? And there's been a lot of arguments over the centuries about what light is. See, originally people thought light was like little particles. So the light is tiny little particles that shoot out from something that produces light, like the sun or a fire or a light globe. And those particles travel in a straight line, hit you in the eye, and then that signal is converted to an electrical signal which goes to your brain via the optic nerve, and it interprets what you're actually seeing. Now, that's not bad, because light reflects and particles reflect. Light, let me turn it back on again. Light travels in a straight line, so do particles, if they're not in a gravitational field, of course. And, different particles could be different colours, that sort of stuff. So not a bad explanation at all. However, light also does some really interesting things, and it behaves a lot like a wave. And waves reflect. Down at the beach, you can sometimes see a wave bouncing off something that reflects. Waves refract, and that's changing direction when they change speeds, and light does that as well. Waves also can be what we call polarized, and we're going to look at that later, but particles can't. And waves can interfere and cause interference pattern, but particles can't. So light has both particle and wave nature. In fact, that's where we've now landed. We've now landed that particle, light is both a particle, very tiny particle called photons, and a wave. Hey, so get your head around that. You don't have to yet. You're only in year 8. All right, now, let's get to the next one. Electricity. Now, you might notice that there's nothing really in here that looks like electricity. There's no batteries or light globes or switches, and that's because electricity is such a big part of physics that Tiny Science Lab has actually produced its own big electricity set and another course, a high school electricity course. So if you want to learn about electricity, this is not the course for you. This is learning about most aspects of physics except for electricity. That's a separate course. But there is some electrical stuff that we can look into here, and electricity is carried by moving charges or charged particles. And we can actually cause some charged particles, electrons, to jump from one object to another. So again, we're going to get out this PVC tube, get out the parachute. Now, the parachute's not silk, it's probably nylon, but I think it still works. Get out the foam ball, one of the polystyrene balls, and first do a little bit of a test where you just bring the PVC tube to the ball. Nothing happens whatsoever. Agree? So this is, I guess, the control part of this experiment. All right, now what I want you to do is rub the PVC tube backwards and forwards on the parachute. Try not to destroy the parachute. Try not to damage it. Like this, rubbing, and then bring it to the... Oh, you're joking. Nothing. You are kidding me. Oh, I did this the other day. Don't you start on me. All right, let's try. So the other day, the interesting thing is, though, that environmental conditions can definitely affect... Oh, there we go. Phew, I thought it wasn't going to happen, but it is happening. Woo! Look, I can walk the dog. I know what happened. There's a little bit of a chunk missing out of that polystyrene ball, and it was like sitting on that broken chunk. Rub. Bring it here. Come on. Way, come for a walk. I'm taking my polystyrene ball for a walk. Come on. Let's try again. Static electricity. There we go. It's attracting the ball. That is static electricity. Hopefully you had success as well. But there's also a very interesting form of electricity, which not many people know about. And you need to get your aluminium tube and one of these magnets. And if I drop a magnet just onto the table, it drops quite quickly. Now, don't drop it onto the concrete floor because it will shatter, right? Where have you gone? What I want you to do is just look down the tube. Notice that it's totally hollow. Okay, it's a hollow tube, and the diameter is bigger than the magnet. But when you drop the magnet through, it goes very, very slowly. Now, that's not because of air friction. That's because you're actually producing electrical currents in the tube, and those electrical currents are producing magnetism, which opposes the magnet falling, or what actually caused the electricity in the first place. So we've just made static electricity and actual electrical currents in that tube. There we go. Now, nuclear. Whoa. Nuclear is energy from the nucleus. Now, what is an atom? Well, hydrogen is probably the simplest form, it is the simplest atom there is. Hydrogen gas, and hydrogen gas in the very, very center has got a proton, and whizzing around it, there is an electron. Okay, so whizzing around the proton is one electron. Now, the electron sort of goes so fast and it's in 3D that it sort of forms like a cloud, like a ball, so it looks like. But in actual fact, the hydrogen atom is mostly empty space. Most of the mass is actually contained in that proton. That proton is like 2,000 times more massive than the electron. Although, interestingly, they've both got the same magnitudes or size charge. The proton is positive, the electron is negative, but the size of the charge is the same, even though the mass of the proton is 2,000 times bigger. And usually in nucleuses are neutrons. And neutrons are also very massive. They're tiny, tiny bit more massive than the proton, because essentially they're almost like a proton and an electron joined together. They're neutral. You know, the positive plus the negative adds together to make zero, cancels each other out, you might want to say. But where does the energy from a nuclear reactor come from? Well, they don't use hydrogen in nuclear power plants. They actually use uranium, which is like loaded up. It's got like 235 nucleons in the nucleus. It's really loaded up. And if you fire in a slow-moving neutron, then what actually happens is the whole nucleus splits into two. But the interesting thing is, if you start off with, let's say, 1 kilogram of nuclear matter, and let's say it does split into two, you actually lose the tiniest little bit of mass. Just the tiniest bit. But that mass is converted into energy according to E equals mc squared, where E is the energy given out, mass is the mass lost, which is tiny amount, but it's times by the speed of light, which is a huge number, 3 followed by 8 zeros, times the speed of light again. That's what E equals mc squared is. And so you can change the smallest bit of matter into the largest amount of energy. And so you can like run a nuclear submarine for 25 years underwater using, I think, just 4 kilograms of uranium. So it's a very power-packed sort of substance. That's what nuclear energy is. And in our sun is a thermonuclear fission device. Fusion. Fusion. Hydrogen atoms actually slam together, and when they slam together, tiny little bit of mass disappears, and that's changed into the energy which produces so much energy that radiates out into all of space. And thankfully on Earth, we get a tiny little bit of that, which is absolutely fantastic. There we go. Now, gravitational potential energy. Now, I've got a picture here of the cart, and you're going to be using the cart quite a lot. And to make the cart, it's very straightforward. If you get the cart like this, pop an axle through. These little round pieces of timber are the washers. And we pop a washer on, pop a wheel on, pop another washer on, pop another wheel on. There we go. Now we've got 2 wheels. Let's get another axle. There we go. Put that axle through there like that. It's just a timber dowel. Grab another piece of foam. Pop that on. Another washer. Pop that on. And action. There we are. Very good. And what have I got here? I've got a piece of string. Okay, piece of string. There's some string here. Woo! I'm going to be using the string a lot as well. And I've tied the string to the cart. Now, there's a few different ways of doing it. And, well, I wonder if I go over the whole thing like that. I'll probably do it too. I've never actually done it like that, but I quite like that. And I'll show you what I've done once I've just tied this knot. There we go. I've actually just gone like that. And whoo, I can take my little cart for a little walk. Come for a little walk with me. Woo. And I can then also attach it to the bottle. Okay. Now try not to smash this cart up because it's just made out of some recycled timber blinds actually. And it might be a bit soft. And so, but if it does break, get out the PVA glue, the craft glue, and see if you can glue it together. And all right, so what am I going to do? I'm going to lift up the bottle, and then drop the bottle. Whoa! Drop the bottle. Look at that. So I am converting, I am converting what we call gravitational potential energy into kinetic energy. Now, where does gravitational potential energy come from? Well, if you have a mass, anything that has matter, which is basically everything, and you lift it up, then you are actually giving it gravitational potential energy. You have to be in a gravitational field, and thankfully we are. It's called planet Earth's gravitational field, and you've got to lift it through a height, and you've got to have mass, and then you have gravitational potential energy. In fact, the gravitational potential energy, GPE, is equal to the mass times the gravitational field times the height. So if you increase any one of those three, you'll increase the gravitational potential energy. Boom, how good is that? So let's pop that away and look at elastic potential energy. Now, obviously, the simplest elastic potential energy is just an elastic band and you stretch it. That gives it elastic potential energy. And you're actually storing it because, you can make change, right? The elastic potential energy causes change. That's the definition of energy. Anything that causes change, well, elastic potential energy can cause change. Now, don't do this to someone else. That wouldn't be very nice. But there's a little Slinky in here. Hey. And it's very, very satisfying. Just be careful with your Slinky. Don't let parts of it touch together or touch other Slinkies, because there's some mysterious force in the universe that causes them to grab together and you can never get them apart again. So just be careful with that. But as it stretches down, then it gets elastic potential energy, which then pulls it back up and turns it into kinetic energy. Ooh, that's very interesting. And I've actually seen these springs going down steps before, and they go, they sort of walk down the steps. Cool, super cool. That's elastic potential energy. We're going to be exploring this spring a lot more in the future. And then chemical potential energy, I've got a magnifying glass focusing in on one of the wheels. And the idea of that is that if you were to heat up one of the wheels, it would actually start to like melt and even burn, start producing heat. Just like when you get a match and you light a match, it's got stored chemical potential energy. There's even some stored chemical potential energy in the batteries in the fidget spinner. So chemical potential energy is the energy due to chemicals and their potential to produce heat, potential to produce light, even they can produce sound as well. So there we go, there's the 9 forms of energy. And now we can look at energy transfers, and that is where energy is transferred from one object to another. So if you get your fidget spinner out and get your finger and flick like this, the finger has kinetic energy, and now the fidget spinner has kinetic energy. The finger has kinetic energy, and it's transferred the kinetic energy to the spinner. That is a transfer of kinetic energy. All right. The first law of thermodynamics, otherwise known as the law of conservation of energy, is that energy can neither be created nor destroyed, but can be changed or transformed from one form to another. Okay, so you can transform, you can change energy from one form to another. So here we go. The chemical potential energy in my body, the muscles, is going to change to kinetic energy, and then that kinetic energy is going to transform into gravitational potential energy. So this ball now has gravitational potential energy. If I drop it, it changes, it transforms into kinetic energy. And then when it hits the table, the kinetic energy is transformed into sound. And we're going to be looking at that a lot more too. And then the second law of thermodynamics, and thermo means heat or energy, dynamics means movement and systems. It's the amount of usable energy in the universe is constantly decreasing. So what that means is you can't create energy, you can't destroy it. You can change it from one form to another. But when I produce this sound, the reverberations go out into the walls. They cause the walls to vibrate, warm up a little bit. That heat is then radiated out into space and it's gone. Can't use it anymore. The amount of usable energy has decreased. The amount of chaos, the amount of entropy, the amount of disorder has increased. So, very, very interesting. Where does the heat go? Out into space, basically. Well, there we go. There's a brief summary on the 9 form on what is energy, the 9 forms of energy, the laws of energy transfers, transformations, the first law of thermodynamics and the second law of thermodynamics. Okay, that's hard to say quickly. Looking forward to seeing you next time. Bye for now, everybody. Hey everybody, welcome to Lesson 2, Investigating Energy, Part 1 of the Year 8 Physics High School course. My name's Jacob and I'm going to be your teacher today. Now, basically the next 3 lessons is we're going to go through every piece of equipment in this set and look at some of the energy implications. So we're really going to do some deep dive exploring. So let's start off with a syringe. And a syringe is used to inject liquids into patients, some type of medicine, that sort of stuff. Don't worry, these are not rejects from the hospital. These are brand new and we don't supply the needle with them. All right, so you can be confident that these things are sterile and safe. Now, there's 2 parts. There's the piston part, and on the piston part, it's got a piece of like a rubber stopper that it's a tight fit inside the barrel or the body of the syringe. So nice tight fit. And what it does is it allows us to, well, it allows to push out whatever's in there. Now, it will push out a gas, it will push out a liquid, but it won't push out a solid. So don't freeze ice in here because you won't get it out. You can freeze ice in here, but that would actually be some interesting experiments as well. But anyway. All right, so first thing is put your finger on the end and then push the syringe in and then release, and it shoots back out. Push it in, and then release, it shoots back out. We're compressing the air particles, and those air particles are moving around and they're colliding with each other, colliding with the wall, colliding with the piston and pushing back. But that's actually storing some energy. That's storing elastic energy. So it's called elastic potential energy, and then when I release it, it changes to kinetic energy. Now let's try something else. Push it all the way in. This time put your finger over the end and pull it. Ow! Ow! Warning, warning. That actually hurts a bit. So don't pull it out too far, all right? Ow, that's actually very interesting. You can store, this pulling it out like this stores a great deal of elastic potential energy, like an extreme amount. And so I've actually seen some YouTubers who like power little racing cars with this principle, where you pull out the syringe and then you use it to pull a string to turn an axle to spin the wheels. So just be a bit careful that you don't hurt yourself like I did. I also make a very interesting noise. If you pull it out like that, not much happens. But if you put your finger over the end, it makes a very satisfying noise. Very satisfying indeed. In fact, when I was a kid, there was some kids who would make this annoying water drop noise by going flicking the side of their mouth, and whoop, makes it sound like a water drop. Anyway, next, you're going to need some liquid, and just can be in a glass, that's fine. I've put a little bit of blue food dye in just so that you can see the liquid. And if I bring in my syringe and draw up the liquid, I end up with some air at the end, which I don't really want. So I'm going to try and get rid of some of, I'm pushing down now, pushing some of the air out. Actually, this will probably be alright. I just dribbled half of it onto the table. I'm going to push that down, and then I'm going to draw it back up. There we go. Can you do that? Can you get a full syringe full of liquid and a full hose full of liquid? No air bubbles in there. Then you can connect it to the other one. Okay, connect it to the other syringe. And we actually have what we call a transfer of kinetic energy. See that? Transfer of kinetic energy. I like it. Okay. So good. Now, if I had another syringe, a 20 ml syringe, which I do. Ta-da! I've got another syringe here, and if I pull this one out, pull this one off and connect this up to it, then again I get a transfer of kinetic energy, but notice a small movement of the big syringe produces a big movement of the small syringe. See that? So the big syringe will go down a little bit and the small syringe will go up a lot. Zoo! Now again, it's a transfer of kinetic energy, but it's very interesting. I can actually magnify the force. I can magnify the force by about a magnification of 2 times. But that comes at a cost. The cost is the piston of the large syringe only moves half as much. So keep that in mind. You don't get something for nothing in science. And then one more thing about syringes I want to show you. This is quite interesting too. I've got the probe of the thermometer inside that syringe. So it's measuring the temperature inside the syringe. At the moment it says it's 23.5. But if I push that down really hard, it just jumped up to 23.8. See that? So by compressing the air, it's gone up to 24.1. By compressing the air in that syringe, I've actually increased the temperature. Okay, well that's enough on the syringes. Now you can pull out the retractable tape. So here's a retractable tape, and firstly, when you pull it out, it makes a very satisfying clicking noise. Tick, 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 tick. Tick, 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 tick. So you're actually changing kinetic energy to sound energy. But you're also compressing or tightening up a spring. And so that converts the kinetic energy into elastic potential energy. So these can actually be used to exert a force over a distance, thereby doing work, and we can use it to pull your cart. So I've built my cart, and see how you've got a funny shaped thing at the front of the cart? That's for the tape to go in, like that. See that? Then if we press the button, we can pull the cart towards us. So we've got kinetic energy. Kinetic energy is used to transform into elastic potential energy, but when I press the button, elastic potential energy is transformed into kinetic energy. How good's that? I love it. And later on, we're going to do an experiment whereby we put different weights. Well, we put a bottle with different amounts of water. Woo! And we're going to see, how changing the weight affects the acceleration of the cart. So I'm looking forward to that experiment. What about the rubber ball? So if I have the ball down there and I pick it up and drop it, whoa, there. Oh, I think it might even come back. I saw it bounce over there and then come back. So if I, bounce the ball, pick up the ball, if I pick up the ball and then let go, a gravitational potential energy up here, it's changed into elastic, not elastic, it's changed into kinetic energy. Okay, it's changed into kinetic energy. But when it hits the ground, the ball squishes. And so the kinetic energy is changed into elastic potential energy as it squishes. And then as it releases that energy, it's changed back into kinetic as it goes up, which then is transformed into gravitational potential. And so the cycle continues. There's also a fair bit of sound produced. Okay, so speaking of which, if you get your steel ball and drop it, that's a loud sound, isn't it? The gravitational potential energy is changed into kinetic energy, which changes into sound. So much sound that virtually none of it changes back into kinetic energy. In fact, what it will do on the atomic scale is it will cause the wood to like flex a little bit, and that flexing, that change of shape, actually absorbs some of the energy. The energy is formed into like the elastic potential of the table, but that's spread out quite far as well. Now I've got a question for you. If we lift up these two balls to the same height, which one do you think has got the most energy? The rubber ball or the steel ball? Well, the answer is the steel ball, because the steel ball has got much more mass. And the gravitational potential energy depends on three things. It depends on the mass of the object, the height of the object, and the gravitational field that you're in. In fact, you can calculate it by saying potential energy is the mass times the gravity times the height. If you increase any one of those values, the gravitational potential energy goes up. So that's our steel ball. Now imagine if this was red hot. That would have a lot of heat energy, and you could do some interesting things there, couldn't you? Now, the magnets. Okay, so I've got two magnets here. They're quite cheap magnets actually. They're very simple bar magnets. And I know exactly how these bar magnets are made because I've seen them made. And what they actually do, they have like they're trays like ice cube trays, but the ice cube trays are shaped like the ice cube's just shaped like this magnet. They pour in powder. And then they compress the powder. And the powder is made up of like iron particles and a glue. And it compresses them in a hydraulic press. And then they pop them out. They're not magnetic yet. Then they put them in this coil of wire and they send through lots and lots of electricity, which turns these into magnets. Now, if you drop this on the ground, which I did, you actually can see the grain. It's like sandy metal on the inside. But I've turned one magnet, into two magnets. Every single magnet has both a north and a south pole. Even if you break it in half, you'll still have a north and a south pole and a south and a north pole. If I could make 4 magnets from this. I could keep breaking it up, and every time I'll have a north and a south pole. But if we bring the south pole of the magnet to this north pole, all of a sudden you'll see that the magnet moves. Now, it takes a bit of effort to pull the magnets apart. Now, when I say a bit of effort, that's actually work. A bit of effort is exerting a force over a distance. If I have to increase the size of the force or increase the size of the distance, I've increased the amount of work done and the amount of elastic potential energy stored. So I've actually got some elastic potential energy stored there, and when I bring in the magnet, all of a sudden that's changed into kinetic energy. So we will be doing a lot more with magnets. Okay, so if you love magnets like most people, we'll be doing a lot more. The spoon and chain. What could possibly be the area of interest here in terms of energy? Well, when I went to banks as a kid, I really enjoyed playing with the chain. The chain was attached to a pen, or the pen was attached to the chain, so you couldn't take the pen home. But I used to love wiggling. the chain on the piece of wood. That's what I used to love a lot. So I'm transferring kinetic energy to kinetic energy. And if I do a small movement, I get like what we call a small amplitude. But if I do a big movement, then I get a big amplitude. So we'll be studying waves later on, but that's a little bit of a taster. And then finally, there's some iron powder. Now, what type of energy can we talk about with iron powder? Well, I don't have iron powder on here, but I've actually got some steel wool. And steel wool is made up of the same particles that iron powder is made up of. And steel wool is basically where they've taken steel and they've stretched it out, ductile, and so it's really thin. It's like your hair almost. And very, very interestingly, if you stretch out steel wool and make it like hairs or fibres, first I have to light this match, of course. What's very, very interesting is it seems to burn. Now, this is what we call ultra-fast corrosion, basically. That's basically what's happening. The iron is reacting with the oxygen in the air to form iron oxide. But once you've converted it all to iron oxide, it doesn't burn anymore. That's the end of its burning. Okay, but basically, steel wool actually has some chemical potential energy, and the chemical potential energy can get changed into heat and light. Well, that's it for lesson 2, Investigating Energy Part 1. Part 1. Hopefully you've enjoyed the lesson, and I look forward to seeing you again soon. Bye for now, everybody. Bye. Hey, Investigating Energy Part 2 of the Year 8 High School Physics course. I'm Jacob, and looking forward to being your teacher today. Wherever you may be, you might be in a remote rural school, you might be on a caravan adventure, you might be home educating, you might be in the hospital. Well, regardless of where you are, let's focus on the physics. So, we're going through all the pieces of equipment in the physics set and exploring their implications to energy. And we've got a little plastic vial here that's got 10 magnets, 5 bigger ones, big, tiny, but not as tiny as those ones, and 5 smaller ones. And these are neodymium magnets, which are made from rare earth materials, and they're very, very strong magnets. And this material, these rare earth magnets have revolutionized society. It's why we can have powerful electric cars, because the electric motors require really strong magnets. It's why we can have tiny little earbud, earphones, because those powerful magnets are required for the loudspeakers. And if we put a little magnet there and bring in the other one, kapow! Now, do have to be a bit careful, word of warning. We don't want them to slam together too hard because they could shatter. Okay, and no doubt these magnets are made by sintering as well. That's where there's a mold and they pour in a powder. They really hydraulic press under a great deal of pressure. I'm pretty sure that's how they're made anyway. Maybe I'm wrong on these ones, but anyway, I know they're rare earth. Now, they can store a lot more elastic potential energy than the bar magnets. Anyway, there we go. We're going to be using these a lot in different experiments later on. So let's pop these down. Next one I want you to get out is the string and the rubber stopper. And I'm going to show you something very interesting. It was actually a home educated, I was at a workshop a science workshop and doing toys. And the toy we were making was basically where you put the kids put the string through the, well, they attempted to put the string through the rubber stopper. I can't even do that. Come on. Blow on it. Make this a bit straight. Push through. Come on. Get to the end. I might try the other side. Maybe this. We burn the ends to stop them from fraying. Yay, I did it. So I was at this workshop, and what we were supposed to be doing was tying off the end of it like this. This is what we were supposed to be doing. And then we were like whizzing, well, let me tie that off a bit better. Tying knots is not my thing, I'll be honest there. Is it your thing, tying knots? And the idea was that we then went outside and we swung it around like this and then let it go, and it like, quite fun actually, but that's not what we're doing. What happened was a kid, after he'd threaded it through, he put the rubber stopper in the middle of the string like that, not to make a necklace, but then he did this. And that in itself looked quite fun. I went, whoa, that looks fun. There's a lot of kinetic energy there, appears to be. I'm just going to wrap it around my fingers a bit for this next part, because if you now pull it tight, it seems to go a lot faster. If you pull it tight, it seems to go a lot faster. Whoa! And then if you let it go loose again, whoa! Very interesting. Very, very interesting. Ooh. There is a conservation of energy. It might appear to go faster, but I don't think it actually is going faster. It's just got a shorter circumference there, because you can't create or destroy energy. But anyway, that was what I wanted to do with you, to show the kinetic energy aspects, and also what we call the conservation of angular momentum. You might have seen like a ballerina or an ice skater where they put their arms out and they do a pirouette, so they're going around, but then they bring their arms in and all of a sudden they speed up. Now that's called the conservation of angular momentum. All right, next favourite thing in this set is definitely the Slinky. And you've got to be careful when using Slinkies, because there seems to be some mysterious force in the universe that whenever a Slinky touches itself or touches another Slinky, they like, they join up, never to be released. So there's a word of warning. Actually, we sell this equipment, and someone, their equipment arrived and they claimed that the Slinky was broken. The Slinky was broken. Now, how you actually break that in transit, I don't know, but what I suspect happened was the kid was playing with it, got it stuck, maybe tried to undo it, pulled it, put it back in, and it had a funny and it wasn't nice anymore, and so they claimed it was broken. Now, being the top guy that I am, I did send them a new one, but I'm not going to send you a new one if you go and break it, okay? You got to look after it. There you go, you've been warned. No more refunds on the Slinkies. Right, because they don't break if they're being used pretty normally. Now, you can change kinetic energy, or you can transfer kinetic energy by what's called a compression wave. So I'm going to stretch it out a little bit, pull one part back, and you can actually watch the wave travel backwards and forwards. We're transferring energy. We're transferring kinetic energy from my finger, here's my finger, to the spring, and then it goes backwards and forwards, but that energy is changed into sound and heat, and so the kinetic energy slowly reduces. You can also do what's called a transverse wave, and whoa, this is actually a really interesting transverse wave. This is the fundamental. But again, by moving my hand, I'm transferring kinetic energy to kinetic energy, basically. There's also like some storage of energy there. We are getting some elastic potential energy stored. But anyway, we're going to look at this in more detail later. Then over here near the plasticine is a round metal dish, and it doesn't have any energy at the moment. But if I lift it up, if I do work on it by pushing it, by exerting a force over a distance, I give it gravitational potential energy. And if I drop it, well, that changes to kinetic energy, which then changes to sound energy. So that's got a nice ring to it, doesn't it? So I wonder if I give it a spin like this. Oh yeah, I can get it spinning again. Kinetic, transfer of kinetic, and then transfer of kinetic to kinetic, and then there's a transformation of kinetic to sound. There's our little stainless steel dish. The fidget spinner. There's a few different energy aspects to this. One is that, that one is not working at the moment. So the batteries on these do go flat over time, and if one sort of stops working, you could actually give a little bit of a push. But hopefully at least one of them works. That's really all you need for this fidget spinner to be effective. But when you turn it on, the chemical potential energy is changed or transformed into electrical energy, and then that electrical energy is changed into or transformed into light. There we go. There's an energy transformation, or plural. And if you hit it with your finger, you're transferring kinetic energy to kinetic energy of the fidget spinner. And it's quite satisfying, isn't it? Over time, that kinetic energy transforms into sound and heat, and so it does slow down. I like it a lot. Plasticine. Plasticine. Now, have you seen the plasticine? Just made that up. Oh, that actually feels quite cold. Now, although it feels cold, so I think this is actually quite interesting, this. If I pick up the piece of foam and feel it, it doesn't feel cold. If I pick up the plastic retractable tape, it feels a little bit cooler. If I feel the spring, it feels coolish, but the plasticine seems cold. Is it colder? Well, the thing is, it's sitting, oh, that light then came on. It's sitting in the same container as all the others, so it should actually feel the same temperature. Well, it is the same temperature, but it feels colder, and that is because it makes a lot of contact with your skin, and because your skin is like at 30 degrees Celsius, which is 10 degrees higher temperature than this, there's a lot of heat transfer from your skin into the plasticine, right? There's a lot of heat transfer. And so that's why it feels cold, even though it's not actually cold. But it absorbs the heat from your skin far more readily than this insulating material. So that's interesting in itself. Now, if you go bang, bang, bang like this, or throw it on the ground 100 times, but don't do that because I don't want to have all dirt in this because you're going to need this later. But if you go bang, 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 this kinetic energy that you're exerting changes into heat. So there's a transformation of kinetic energy, that's the movement energy, into heat. And also, when you drop it, it doesn't bounce very high. That's because there is some there's some deflection. In the collision, there's some deformation. The materials have deformed, and when you're deforming material, and a deformation is like a permanent change in the structure, you're actually causing an increase in elastic potential energy. The big thing here that I'm hoping that you're picking up on is that you can't create energy and you can't destroy energy, but you can change it from one form to another. That's the big thing I'm hoping that you pick up on. And finally for this lesson, the foam ball, is why doesn't it fall, if I pick up the foam ball and drop it, why doesn't the foam ball drop at the same rate as, say, a steel ball? Or does it? Which one, if I drops fastest? Interestingly, they both drop fairly similar speeds. If I get the rubber ball and the steel ball, they effectively drop at exactly the same speed. And we're going to talk more about that later and do some investigation. Is why does a heavy ball fall at basically the same speed as a much, much lighter ball? But we're going to investigate that. Now, if you were to burn this ball, which is not a good idea, but if you were to burn this ball, then chemical potential energy is changed to heat. Now, some of you maybe have not done the year 7 physics course. You've just jumped straight into the year 8 course. And that's okay. I'm not judging you. Okay, don't you worry. But there's this funny piece of foam here. Now, this was used in the year 7 course. And there's also a flexi straw. Now, if you bend that flexi straw at right angles like that and push the straw in like that, see that? Then, if you get the ball, you can blow on the ball and give it gravitational potential energy. So to lift it up, a force is required. The force comes from the particles of my breath blowing onto the ball and pushing it up. But in actual fact, gravity is pulling the ball down, and it gets to a height where the two forces are equal. The gravitational force down, the weight force down, is equal to the force of blowing up. And then it doesn't accelerate anymore. It doesn't change its velocity. And so it just stays there until you remove, of course, the air blowing up on it. Well, that is it for this lesson. Lesson 3, Investigating Energy Part 2. Thanks for joining me today. Hopefully you've had a good lesson, enjoyable lesson. You've learned a few things, and we'll see you again soon. Bye for now, everybody. Bye-bye. Hey, welcome to lesson 4 of our year 8 high school physics course. In this lesson, we're going to be continuing our investigations into energy. Remembering energy is anything that causes change, and we're up to part 3, and we're going to finish going through the relevant pieces of equipment and looking at the energy implications with those pieces. So we're up to the pipette, the plastic pipette, and we're going to, for this lesson, there will be a few extras required if you want to do all the activities that I'm doing. One of those extras is a kettle with some very hot water. Now, hot water is quite dangerous, so just bear that in mind. Hot water is very, very dangerous. You might want to have parental supervision. And another thing that you could have is just a bottle with some vinegar and some bicarb. Otherwise, I think that should do it. So, the plastic pipette. Now, if I take a little bit of water and squeeze the pipette, I'm squeezing the air out of the pipette and then releasing it, water goes up. Now, believe it or not, I'm not sucking up the water. Believe it or not, the water is being pushed up by air pressure around us. Now, if I want, I can squeeze the pipette and the water shoots out. I am transferring kinetic energy from my fingers to the kinetic energy of the liquid. Now, I was in taking a class once, and a year 9 boy came up to me. I believe his name was Oliver. No, not Oliver. It was his brother, Lucas. Lucas came up to me and said, "Oh, Mr. Strickling, I think I've made a discovery." I went, "Oh, what is it?" He said, "If you suck up some hot water with your pipette and turn it, it squirts out." Anyway, I thought that was very interesting. And so I thought I'd better investigate this myself, this phenomena. And it turns out he was absolutely correct. So I've just turned on the kettle, because for this phenomena, you need super hot water. Okay? You need super hot water. And I've got my pipette here. I'm just going to put in a drop or two of red food colouring, and then the kettle's been boiling away. Pour in the hot water like that. That's super hot, and you've got to do this fairly quickly. But you draw up the water and then twist it. Whoa! And then when you twist it, well, actually it's changing the properties of the pipette, that's for sure. It's making the pipette go quite soft. Heat changes the property of materials. Now, it will cool down quite quickly. I'm going to try and draw some up again, and then I twist it, and it comes out by itself. In actual fact, I've seen them squirt fairly far. This one's not squirting very far, but it certainly squirts out when you bring it up. So don't squirt it towards your laptop or your iPad if you're watching this on a laptop or iPad. But the heat heats up the air here, causing it to expand, pushing out the liquid. Now I need to move this quite carefully because that was hot. Now if you ever do burn yourself, cold water is the treatment for that sort of burn. Alright, so the next one is our aluminium tube and magnets. So we've got your aluminium tube here and the neodymium magnets. This is absolutely fascinating. I can do this over and over and over again. But if you have a look down the tube, you can see that it is hollow. Now that's actually really interesting, me looking down this tube now, because I'm looking at the camera, and on the camera is a really bright LED red light. And as I look at the LED light, I get this circular pattern travelling up the tube. So I'm actually looking around like using this as a telescope. Now, do you know what happens if a telescope and a microscope collide? You get a kaleidoscope. Anyway, yeah, maybe you don't get that. I think it's a funny joke. I saw it the other day. There we go. Okay, so anyway, that's that tube is hollow. Then take one of the big neodymium magnets and drop it, and it comes out. Now, I've worked out a little bit of a trick, you know. You want to do a trick with someone? What you can do is you get that metal plate, right? And you hold the metal plate in your hand so that people can't see the metal plate. Then you put the plate on the tube like that. Then when you drop the magnet, doesn't come out. And then you say, ready, set, come out. And then it drops out. Look at that! I've just taught you a magic trick. Okay, so let's do it again. Without the metal plate, if you drop it, it takes quite some time to come through. This would actually work. You could do this trick better if you actually had a ring that was made out of iron, because then when you put the ring next to the plate, when you put the ring next to the tube, the magnet is attracted to the iron ring, and then it stops. I don't wear iron rings. I wear gold rings. you know, yeah, fancy as me, you know. But what I'm thinking is I could actually wrap this chain around my finger, not too hard, of course. There we go. Look at that. What a beautiful looking. Look at that. Oh yeah. How good's that? I might tuck the spoon into my other ring. There we go. That way you don't see it. I don't know whether I can tuck that in or not. No, not easily. Anyway, so this time I'm not going to use the steel plate. I'm going to use that chain. Oh, you see the spoon hanging there? That's a bit of a problem. And then if I drop it, oh, doesn't come, doesn't come, doesn't come. Everybody ready for it to come? Ready, set, move your... Ta-da! There we go. What are the energy transformations? Well, the energy transformations are, of course, if you drop something and it falls due to gravity, you're converting gravitational potential energy into kinetic energy. So there's your first one. Then it becomes really complex with the aluminium tube. Basically, are you ready for it? The magnet induces an electrical current in the aluminium tube. The electrical current produces a magnetic field, and the magnetic field opposes the change that causes it, which is the movement of the magnet, and so it slows the magnet down. Now that's to do with the conservation of energy, the first law of thermodynamics. Okay, if you're producing electricity, that energy has to come from somewhere, and it comes from the speed of the falling magnet. Perfect. Okay, the drinking straw says twist, flick, and pop. Okay, twist, flick, and pop. Now, you can only do this with a drinking straw, but it only works with a plastic drinking straw. Now, President Trump has recently, so this is I'm filming this early 2025, has recently signed an executive order in the presidential office bringing back plastic straws, because he claims that paper straws, one of their many problems is that they explode. Okay, I've never seen a paper straw exploding. I've certainly seen them like go droopy and fall apart and that sort of stuff, but never explode. But I can actually make a plastic straw explode. Now, to do this, you need two people. Me, being the talented person that I am, might be able to do it with the one person, me. But this is what we do. We squeeze, and it destroys the straw, by the way. So choose wisely whether you want to do this or just watch it. At the moment, what's it full of? Full of air. Air is something. Don't say nothing. Don't say, oh, it's got nothing in it. It's got air in it. That's significant. So when I squeeze off the two ends, I'm trapping the end. Squeezing it, and then I go like this, and I'm twisting. Oh, that's actually quite difficult to do. I'm twisting it around, and as I go around, I'm making the straw shorter and shorter, and so the pressure inside is getting bigger and bigger, and somehow I have to now flick that, and it did. It exploded. It popped. Not very loud, that one, but not too bad. But when you pop it, when you flick it, there's extra pressure involved, and those air particles explode out of the straw. Now I have destroyed this one-use plastic straw, unfortunately, but it was for science. It was for your education. So leave me alone, please. Now I used to have a spud gun where you push a spud gun into a potato. Spud is another name for a potato, and then you squeeze the handle, and the air pressure pushes out that little piece of spud from the potato. All right, the next one, you should have a plastic ruler. Okay, plastic ruler in your set, and if you put that down onto a table and release it, you can actually produce a type of sound. Whoop. How good's that? And if you've got different lengths, then when you do the different lengths, you get different frequencies of vibration, which reminds me of a very interesting toy that I'm going to get and show you. Back in a moment. Ta-da! It's a music box. Now let me play some music for you. Do you know what that music's from? Star Wars! How does it work? Well, the ruler vibrates at different frequencies depending on the length of the ruler hanging over the table. When it's very, very short, the frequency is very, very high. When it's very, very long, the frequency is very, very low. The music box has got all these metal prongs which are slightly different in length to each other. They're called steel combs. And when I rotate this handle, there's a drum that goes around. It's a cylinder drum, and it's got these little raised pieces of metal. And as they go past each of those, we'll call them tines, that's the steel prongs, it lifts them up and then releases it, and they vibrate. And when they vibrate, they produce a sound. And so they can do several at the same time, and they'll choose which one to, it's sort of pre-programmed to lift each one at the right time for the particular frequency to make the music. So now it's not as loud when I hold it, but it's much louder when I put it on the timber table. And the reason is the whole table vibrates, and when the whole table vibrates, it vibrates all of the air around it. And then that's a lot of air vibrating, which is a lot of sound, which gives us a high amplitude or volume. There we go. The ruler. Energy change from kinetic to sound. All right, next, the elastic bands. Well, there's quite a few different elastic bands. And when you stretch an elastic band, of course you get elastic potential energy. But if I fire it towards the ceiling, pew, then it shoots up, pew. I might even do one of these larger ones. You might have a large black one, or a large orange one. There we go, I caught that one. Might do it again. Boom, woo. Hey, that's quite a fun game. Shoot! Don't shoot this in your eyes though, or someone else's eyes, because it could hurt. But basically, the elastic potential energy changes into kinetic energy, and then that changes into gravitational potential energy, and then when it starts falling, it changes back into kinetic energy. So many energy changes, yeah. Balloons. Oh, balloons are wonderful things as well. If I blow up the balloon, I've got elastic potential energy, and if I release the balloon, I get kinetic energy. But I've also can show you some chemical potential energy, and so that's why I've got some bicarb soda, which I'm just going to put into the balloon. So I've made a little bit of a funnel here by squeezing the end of that paper, and this way I'll get some bicarb, hopefully some, yeah, it's going in. Whoa, it's going in into the balloon. I can feel that, look at that. There's a wad of bicarb there. And then if I get my bottle, and now you could put some citric acid in here. Don't use up the citric acid in your set though. Is there citric acid in this set? No, there's no citric acid in this particular set. So, but you could use citric acid and water, so you can make your own liquid acid, or you can just use some vinegar. Okay. So I've actually got some chemicals So that probably means I've got some chemical potential energy. The potential to do or to produce or have a transformation. Oh, whoa! Here we go. I'm having chemical potential energy transforming into what? Hopefully you said elastic potential energy, because that would be correct. And interestingly, this does cool down a little bit. This is an endothermic chemical reaction. A lot of chemical reactions produce heat. Some chemical reactions actually absorb heat. And so now I've got a balloon full of carbon dioxide gas. And if I release it, whooey, the elastic potential energy gets changed to chemical potential energy. Well, thanks for joining me today. Hopefully you've enjoyed this lesson, and I look forward to seeing you again soon. Bye for now, everybody. Bye-bye. Pew, pew, pew! Have you ever watched Star Wars and seen the stormtroopers like shooting away, never hitting anything? Well, today we're going to make a little piece of equipment that's going to sound like a stormtrooper's laser gun. So, welcome to lesson number 5. It's the Stormtroopers Pew Pew Laser Blasts lesson of the Year 8 High School Physics course. I'm Jacob, and I'm looking forward to being your teacher. There's a lot of responsibility there. Guide? How about just... I'm going to lead the lesson today anyway. Alright, so you're going to need a few things today. A pair of scissors. Careful, scissors are generally sharp. Toilet roll paper holder. And this is a cling wrap tube, empty. And I found a plastic piece of pipe as well. Now this might be a little bit harder to find. You certainly should be able to find some cardboard tubes around the place though. So we're sort of doing energy, and we're going to investigate some sound energy with this. So let's get a balloon out, and with the balloon you got to like cut off like the bottom nozzly section. Okay, now you can always cut off more if you need to, but it's very difficult to cut off less, if you know what I mean. Now, let's pretend it's like a swimming cap, okay? This would be a swimming cap for Barbie, but you get your top of the balloon and you can put it over the cardboard tube. Now, I've got some sticky tape on the picture here, but you don't actually need sticky tape, which is great. So that you end up with a rubber diaphragm over the top of the cardboard tube, and I wonder if I get the foam ball. I'm just interested whether I've made like an air cannon. Not a very pretty ordinary air cannon. That's not moving much air at all. Oh, it's actually moving a little bit. Let's do this a bit more. Pew! Okay, now get your spring, and you'll see at the end of the spring there's an end of the spring. So you sort of lift that end out, but not too. Don't exert too much force on it. We don't want to wreck the spring. We want it to go back to its perfect compact self later on. We don't want a piece of the end like lifted up. We don't want to go past what we call the elastic limit of the spring. Now, the elastic limit of the spring, that if you stretch it, if you're within the elastic limit, then it will go back to its original shape, its original length. But if you stretch it beyond the elastic limit and go into the plastic limit, then it won't go back. All right, and then your spring will look a bit dodgy. All right, so get the And the reason, look, to be honest here, the reason I go into that sort of detail, it's not so much that I care about springs, but understanding the elastic limit, the plastic limit of substances and materials helps us understand the world around us, right? It's not just about the spring. It's about bridges. It's about structures, right? So, there we go. Although I do care about the springs. So, the springs. Okay, you take that sharp bit and you poke it through your finger. No, don't do that. You poke it through the balloon and be careful that you don't poke it through your finger because it's quite sharp. Okay, so don't poke your finger. Well, hey, I got it through the balloon like that. And so now, if I turn it upside down, I can hang the spring off the balloon. And I can already hear something interesting. But I'm going to bring this over to you and hang this over the desk. And are you ready? Here we go. Does it sound like a laser blaster? Pew, pew. Let me have a listen. Not bad. Now, when I say not bad, that then leads to a little bit of an experiment. Is there a way I can make it better? You know? Can I make this sound better? Can I make it louder? So one thing I might do is stretch it even more over the balloon and make it a bit tighter. Let's try that. Is that a bit louder? Or what I can do is say, what happens if I use a different length cardboard tube? So I'll take that cardboard tube off and get the cling wrap tube, which has got a very similar diameter. It's just a lot longer. Will having a lot longer one make a difference? That's an interesting question, isn't it? So let's try this. Now the end's a little bit weak, so it's not quite stretching it as much, but let's try this one, hey? Let's see if there's a difference. Is there a difference? I think so. It's a little bit louder. Let's try now the plastic, the PVC tube. This is a piece of like sewage, sort of stormwater, some type of plumbing pipe. There we go. Let's try this one. Not stretched as much as I would like, so I'll stretch it a bit more. Let's try this. I think that's made a huge difference. It sounds deeper, but it also sounds louder. Definitely. This has definitely made it a lot louder. I love it. So we've just done an experiment because we've changed a variable. We've changed the tube. We've tried to keep everything else the same balloon, the same stretchiness, the same spring, but we're changing both the material and the length of the actual tube. It would be good if I was to cut this the same length, and that way I'm only changing the material and not the... However, saying that, I do have a pretty similar length there. But if you want to make a fair and valid experiment, you should only ever change one thing. So, I should have had these exactly the same length. They're pretty close, but I should have had them exactly the same. And that changes just the material. And I should have actually had a cardboard tube, which is the same length, to compare the material, and let's see how much of a factor size is. Anyway, I'll leave that up to you, and thanks for joining me today, and I look forward to seeing you again soon. What was the energy transformations, by the way? We started off with like kinetic energy, the movement of kinetic energy, and that there was actually a bit of like potential energy there, gravitational potential energy, but it definitely produced a sound energy. Okay, all right. Bye for now. Bye for now, everyone. Bye. Hey everyone, my name's Jacob Strickling and I'm going to be your teacher today. We're doing the Year 8 High School Physics course together, and today's lesson 6, Newton's first law. Now, Newton refers to Sir Isaac Newton, very famous physicist, mathematician, all-round genius in England in the olden days, and had so many contributions to physics that you could probably call him the father of physics. In fact, a huge branch of physics, the original branch of physics is known as Newtonian physics or classical physics, and we're going to be looking at what we call his 3 laws to do with motion over the next 3 lessons. And so we're going to start with Newton's first law. And basically, Newton's first law can be summarized up by saying that the tendency of an object or body at rest to stay at rest, and the tendency of a body in motion to stay in its motion. So, for example, if I put this bottle here, it has a tendency to stay exactly where it is. It's got a tendency to stay at rest, not moving. I mean, it would be very, very surprising, let's say I put this rubber band over it. Let's say that you couldn't see the rubber band, right? Let's say it was a string. Be very, very surprising if you looked down and all of a sudden you saw this thing moving apparently all by itself. That's because our brains know that for something to start moving, you need to exert a force on it. We'd be looking for the hidden string, the hidden magnet, the blowing of air from the side, something like that. We'd be looking for a force because we know that objects at rest tend to stay at rest. So, let's do a little bit of a demonstration. Now, I think for this demonstration, I can't use this bottle. I have to use a PET bottle. So, if you've got a PET bottle, that would be really, really good. And you're going to need this PVC tube thing that I made, just for you. And you'll notice that there's a little drill hole. That's the top. So you balance the PVC tube there on top of the bottle. Then you get the steel ball, which has got quite a lot of mass. And because it's got quite a lot of mass, it's got quite a lot of inertia. That means it's got a greater tendency to stay at rest or a greater tendency to stay in motion compared to something fairly light like a rubber ball. Then the idea is that you you put the ball at the top. So we've got the steel ball, the PVC tube, and the plastic bottle, and they're all at rest. They've all got 0 kinetic energy, and they've got a tendency to stay at rest. I'm going to flick the PVC pipe out that way. as quickly and as hard as I can, and we're going to see hopefully what happens. So I'll hold the bottle and I'm going to... Oh! Didn't work. Let's try again. Oh, I would have loved that to have worked first time. Let's try again. Put the ball there. Okay, let's put it at rest. Okay, are you ready? Hold the bottle. Yay! Success. Okay, took 2 times. That's okay. I feel pretty chuffed about that. Now, you might say to yourself, hang on, Jacob, the ball did not stay at rest. The ball dropped down. Well, that's because there was no ring there pushing up on it anymore, and gravity's pulling it down the whole time. But notice that it dropped straight down. Notice that the ball didn't shoot off that way. So, yeah, the ball tended to stay at rest in the horizontal direction, but its vertical direction, it accelerated because there was, the only force acting on it once the ring was gone was gravity acting straight down. It's got a tendency to stay at rest. That doesn't mean it will stay at rest. If you change the force situation acting on it, then things could change. All right, so let's do another one of these tricks, shall we say it. So let's get a playing card out. There should be a playing card in your set. You might have a coin. I've got a 10-cent coin here. Okay. Now, there might be a 10 cent, there might be a 5 cent. If not, you can go look for it. Or you could even possibly use this metal disc. But I'm using a 10-cent coin because a 10-cent coin has got more mass than a 5-cent coin. It's got more inertia. So, what we do now, we take our index finger, pop the card on it, and balance the card on the finger. Put the coin on the card, and then I'm going to look at that. Oh yeah, the coin stayed at rest on my finger. I love it. I'm going to do it again. Oh, okay. Balance the card. I've got 2 cards. You've probably only got one. No, I think we put 2 cards in each one. Anyway, here we go. Ready, set, watch the coin. Woohoo! The coin is at rest. The coin has got a tendency to stay at rest. The card was at rest too, but I flicked the card away with a force. Newton's first law. Gotta love it. Objects at rest tend to stay at rest. And you know what? Little demonstration here, but if you get your cart, I've made up my cart, and if we get some plasticine like this, and I'm going to make a little bit of a person. So here's the body. I wonder if the person can be just like that tub. Yeah. So might just put the piece of, I'm thinking about how I can make like a little person sort of thing. Okay, so I'm going to put the tub sitting, that's the person's body. That's good. Then I'm going to do his head like this. Okay, that looks exactly like a person. Now, imagine if you're driving along, boom, 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 and you come to a traffic light and it's red. Put the brakes on so you're at rest. Here's the traffic light. The car's not moving, you're not moving. But there's a car behind you going really fast, not watching the traffic lights, looking around, and slams into you. What's going to happen? Well, the car is at rest, so the car will tend to stay at rest. So if your car gets hit, the car will go forward. Yeah, the car gets pushed forward. And so the car will get pushed forward. But you are sitting in the car and your head is at rest. Yeah, your head is at rest. Now watch that head when I slam into the car from behind. Did you see that? I'll slow it down so that you can see it. I'm going to do it again. Ready, set. Did you see that? I'm going to do it once more. This is incredible. Oh, that was much so. This is a little bit of it. I'm going to rest the head on the edge of the plasticine like that. There we go. Here we go. Ready, set. Look. Look at that. The head tended to stay where it was. The car went forward and the head dropped down here. Now, don't be scared. I'm not talking about your heads falling off in a car crash, okay? But what I am saying is that, do you know what one of the first safety features in a car was? And you're probably saying seatbelt. Well, in actual fact, headrests are very important. The back headrest, because they are so that if your car is hit from behind while you're waiting at a traffic light, the headrest actually pushes your head along with the body. Because if it doesn't, you get what's called whiplash. So what actually happens is, here I am minding my own business, listening to the radio, waiting for the lights to go green when I'm hit from behind, and the car goes forward, which pushes your body forward, but your head stays where it is, and then it stretches back like that, and then the muscles whip it forward. So your head gets whipped forward, and then the tendons and things pull it back, and then it gets whipped back. And you end up with an injury called whiplash if you don't have a headrest. And when I was a kid, lots of people used to have these foam rings around their neck to stop their neck from moving, and you knew straight away they'd been in a car accident where the car had been hit from behind and they had whiplash. And that's how old I am. Back in the day, the cars didn't have the headrest, and so everyone used to get whiplash. But because of that important safety feature, people don't get whiplash very much. So isn't that good? All right, now what about the second aspect of Newton's first law, and that is that an object in motion continues to stay in motion. So you need a balloon. You can probably find a coin. Now, if you don't have a coin, just go get yourself a 5-cent coin. Okay, you can do this with a 10-cent coin for sure. Okay, but a 5-cent coin is pretty good. And put the 5-cent coin in, and then blow up the balloon. That's a good size, actually. Not too big, not too small. And then hold the balloon with your hand here, and then give it a spin and get the coin spinning in the balloon. The coin has a tendency to keep moving. Look, that once it's going, it tends to stay moving for quite some time. It's very, very interesting. This coin is actually undergoing what we call circular motion. How fast can you get it going? As it slows down, though, it tends to come down the hill, and what's actually happening now is gravitational potential energy is being converted into kinetic energy. Let's have a competition. Who can keep the coin going for the longest? Okay, ready, set, here we go. I'm going to say ready, set, stop, and then you've got to stop moving, and let's see who goes the longest. Ready, set, stop. Okay. Mine's still going. Is yours still going? Mine's still going. Is yours still going? It's making some cool noises here. Mine's still going. No cheating. Got my eye on you. Ooh, I can feel it on my fingers now. Mine's still going. Only just. Only just. Still going. I've never actually held it here for so long and watched it stop. And still moving. Stop. There we go. Who won? Me or you? Don't know. But the coin has a tendency to keep going, but it also has an energy transformation from gravitational potential to kinetic. All right, next. Whoa. Okay, need another balloon. Now, we sent out 3 balloons in these sets, but I think as you do the courses, you're going to need more balloons, I'm afraid. Anyway, that's life. Blow up the balloon again. Now, if you know how to undo the knots of these balloons, you could probably rescue that one from before. Then, get the string, and tie a knot in the string. And hold the string here and play a little game. And this is the game. Boop, 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 boop. I'm going to shorten my string a little bit. Oh, it's hit me on the nose. An object in motion tends to stay in motion. If I didn't have the string, then when I hit the balloon, it will keep going. Woo! I've got to come and grab it, all right? If you don't have the string, once the balloon's going, it will keep going in that direction. The string is so that I can pull it back, yeah? And then it would keep going back, but then I can give it a punch, and then it heads back that way, yeah? So the string is very important to stop the balloon and help it to come back. That's why we need the string, yeah? Very, very good. So, if we were in outer space, there was no, gravity might be negligible, no air friction. You know, if I was to get this ball and throw it, then the ball will just head off in a straight line at the same speed forever and ever. Amen. Now, if you're an astronaut and you're walking on, a rocket ship that's coasting along, it's travelling at the same velocity, in the same line, in the same direction, because of Newton's first law. Okay, you don't need to have your rockets on in space to keep going. Once you're going, you just keep going. That's Newton's first law for you. And you'll keep going in a straight line if there are no forces acting on you. But if you hop out of the spaceship and go for trying to fix something up, but your tether breaks and all of a sudden you sort of accidentally push yourself off the spacecraft and you start drifting away from the spacecraft, then you're in a lot of trouble, aren't you? Because you're going to keep heading in a straight line, away from the spacecraft. You've got to do something to get back. And when we look at Newton's third law, we're going to find out what you can do. So back to our cart. And back to our little man. Oh, look at here. I've got a picture of a guy who's got the foam thing on his the neck there. So we'll set this body up again. And this time we're going to have a different type of car accident. This time we're going to be the car in the back. We're going to be the car that slams into the car in front. Looking around. Right? What happens then? Actually, I might even load up make him like this time. This can be the person. I'm going to make him out of plasticine. I don't want that plastic body anymore, and I'll explain why. There we go. There's the person. We need to give him a head, so let's give him a a mouth. Let's get this thing here. Oh yeah, there he is. Look at that. Let's put him on there. Okay, so I've got a big worm driving the car. And what's going to happen is it's going to slam into the wall. Alright, did you see that? The person keeps going. Okay? The object in motion, which happens to be the car and the person, has a tendency to keep going. The car stops, but the person keeps going. Why? Because Newton's first law. An object in motion has a tendency to stay in motion. Now, what should he have on? Seat belt. The seat belt exerts a force to slow him down and stop him with the car. That's why seat belts are so very, very important. So, in actual fact, Newton's first law, inertia is great, you know, and tendency of an object at rest to stay at rest, and the tendency of a body in motion to stay in motion. But the actual definition is even better, and that is, an object will continue at the same speed in the same direction unless an unbalanced force acts on it. So, an object at rest, that's zero speed, will stay at rest unless an unbalanced force acts on it. Now, what are you talking about an unbalanced force? I'll tell you, right? Because I'm here to teach you. Let's say there's a ball there sitting on the ground and two soccer players come running up to it because they want to kick it. And they both kick it at the same time. Bang! Well, that's a balanced force. That's not going to change its motion. An unbalanced force would have been if one soccer player runs up and kicks it. That's an unbalanced force. So balanced force, two forces, opposite direction, same size, that's balanced force. That's not going to change its motion. But you could have an unbalanced force here or an unbalanced force here, and that will change its motion. Or an object travelling at the same speed in the same direction will keep going at the same speed in the same direction unless an unbalanced force acts. And the unbalanced force could be gravity. See that? It could be gravity changes its direction. Woo! See that? Gravity can even change something's speed. Or you might have a rocket ship and the rocket engines turn on. That will change its speed. That will change its direction. Okay? So if anything ever changes speed or direction, we know that there must be a force acting. Well, how good is Newton's first law? Hopefully you've learnt a lot, and I look forward to seeing you next lesson. Bye for now, everybody. Bye-bye. Bye-bye. Hey, we are up to lesson 7, Newton's second law. Sir Isaac Newton, famous English physicist, mathematician, was big into describing the properties of light, developing extremely important tools for mathematics, looking at motion, forces, that sort of stuff, gravity. And today his second law has to do how a body's motion changes according to the size of the force acting on it and according to the mass of the object. So, you know, if you push something harder, we know it speeds up more, you know. And if it's heavier, then when you give it a push, it's harder to move it. Well, we're going to mathematically look today at how changing the mass of an object, the amount of matter, affects how that affects its change of speed when we use a constant force. So the force we're going to be using comes from the measuring tape, okay? So when you pull it out and press the button, the measuring tape pulls, and that's what we want. It's a fairly constant force. It's not perfectly constant, but it's not too bad at all. And of course, you're going to need your cart. Now, don't forget when you build your cart to add the little wooden spaces, okay? Now, if over time the hole on the cart becomes a bit loose and the wheel falls off, well, then you can start using a different size wheel. You can start using like the medium size or even the small size. You don't always have to use the same size wheels, okay? So next, I'm going to attach the front of the tape to the front of the car and pull him out like this. And ideally you want to pull this cart over a distance of like 1.5 meters. And it would be really good if you had some help, okay? Now, I don't have anyone to help me, and so I actually need a stopwatch for this activity as well. But let me see if I can find a stopwatch. Back in a moment. Alright, so yes, you need a stopwatch, but you can actually use a mobile phone as the stopwatch. Now, the reason I'm not using my mobile phone is my mobile phone is right there filming this worksheet for when I fill it out. So, a mobile phone is perfectly good for the stopwatch because we need to time. And this is a great activity to do with someone else, okay, to get some help. One person pressing the button and the other one timing it, that sort of stuff, okay? So, I'm going to do my best. But it'd be better if you can do this with help. And so we're going to plan this experiment. All right, we're going to plan this experiment. And to plan the experiment, I like to use the lotus flower approach. Now, you can't really see the flower here, but in the center of the flower is the independent variable. That's the thing that we are going to change. So what are we trying to do? Well, what's the aim? What is the relationship between the mass of an object, in this case it's going to be the cart with the water bottle on top, and its acceleration? And the acceleration is how quickly it changes speed when a constant force is acting. Now, the constant force in this case is going to be applied by the spring. So, what are we going to change? The mass of the cart. How are we going to change it? Well, we're going to be putting a bottle on it. Okay, so let's put the bottle on like that, and let's attach that bottle with an elastic band. There we go. So now the bottle won't come off, which is really good. And that by itself, the cart and the empty bottle by itself actually weighs 50 grams. Okay, so that actually has a mass of 50 grams. So keep that in mind for later on. What are we going to change? Well, we're going to be adding 50 ml of water, 100 ml of water, 150 ml of water, 200 ml of water. And so I've got some water, just some water here, coloured blue, that I can fill the bottle up with. No problems at all. What are we going to actually measure? Well, we're going to measure the time it takes for the cart to travel from one place to another place. And I'm going to actually do a measurement. My distance that I'm going to measure is actually, I'm going to do it over 1 metre because my table's a bit short. But you can do it over 1.5 metres because you'll be able to have a lot, you can do it on the floor, yeah? But what are we going to keep the same? Well, we've now got to keep everything else the same. We're going to be changing the mass, but now we want to keep everything else the same. So we're going to keep the size of the wheels the same. Now, if you're using the medium size wheels, then you're not going to have large. You're going to cross that out and put medium. The surface. Well, I'm going to do it on a tablecloth on a wooden table. So I'll put tablecloth on wooden table. There we go. That way I can repeat it later on if I want to. I can remember what the condition there. The force applied by the retractable tape. So I'm going to make sure that I use the same tape each time, not a problem. I'm going to make sure that it's a flat table and it stays flat, that it doesn't change its gradient or its slope. The distance through which it's pulled. Now, I've written here 1.5 metres, but I'm, in this experiment, just going to do it over one. I might do it over 1.1 metres, you know, because the further that you can do it over, the more accurate your results are going to be, because the further it is, the longer it takes, and so your stopwatch errors will be minimised compared to the total distance. So I'm going to do it over 1.1 metres. You do 5. You do 1.5. The axles, I'm going to use timber dowel axles the whole time. I'm going to be using the timber washers the whole time. Is there anything else that I haven't thought of? You know, it might be, I'm going to do it in a still room. Okay, in a still room. I don't want any wind in the room, because if I have some wind, it might produce some wind currents that push on it that affect it. Does that make sense? Okay. So, I'm going to now attach the stopwatch. Not the stopwatch. I'm going to attach the tape measure. Like this. I'm going to put my cart here. I'm going to look at the measurement here, 1.1 metres. That's it. And I'm going to have my stopwatch ready on 0. And then I'll press the button. And when it hits the end of the tape, I'll stop the stopwatch. Ready? I'll straighten it up. Ready, set, go. Ah, silly me. You know what I did? my brain just pressed that and it didn't hold it down. I have to tell my brain to hold the button down the whole time. Brain, hold the button down the whole time. I'll try that again. Here we go. Ready, set. All right. 0.59 seconds. Now 0.59 seconds, that's good. Let's go 0.59 seconds. That's actually a little bit more than half a second. So now let's do a second trial. Okay, let's do a second trial. I stretch it out to 1.1. You'll stretch it out to 1.5. Ready, set. And 0.62. 0.62. That's actually an incredibly similar value, believe it or not. That 0.59 and 0.62 are very similar values. Alright, and reset. Oh, stopwatch didn't work and it just hit the side of a set there, so that's not good. I'm going to have to replay that one. 1.1. And oh, my stopwatch didn't work. Pain in the neck. That's life. These things happen. .62. Wow. Now, how do I get an average? Well, I add the three numbers together. Okay, so I go 0.59 plus 0.62 plus 0.62 go equals, and then I divide it by however many numbers I have, which is 3 divided by 3 equals 0.61. Now, does that make sense? Yes, it does. That's a little bit more than the lowest and a little bit lower than the highest. So 0.61 is my average time. And what's the acceleration? Well, I've got a formula here for the acceleration. The acceleration is 2 times the distance over the time squared. Now, that formula is beyond the scope of this course, working out that. That's if you're doing year 11 or 12 physics, or maybe if I do it in the year 10 course. I'll probably do it in the year 10 course. So for me, this is what I'm going to do. I'm going to work out the acceleration straight away. So we'll go 2 times the distance. What's the distance? For me, it's 1.1 equals, so I get 2.2. And then I'm going to divide that by the time squared, which is 0.61, and I press the square button and I go equals, and the acceleration is 5.9, which is actually quite high. 5.9 is actually quite a high value because the acceleration due to gravity is 9.8, and so that's less than 9.8, but it's more than half, but that's okay. All right, that was 50 grams, that's the empty bottle. Now we want to do 100 grams, which is the empty bottle plus 50 ml of water. So notice there's some lines on the bottle. Okay, those lines on the bottle there, each line represents 50 ml. So, perfect. I'll screw the lid on. Screw the lid on tight. And make sure the wheels are all good still. Everything's spinning good. Okay. Yep. We don't want any extra friction. We need to keep everything the same. Okay, everything's got to be the same. The only thing we're changing is the mass of the object, which is the mass of the bottle. Put that to 1.1 and reset my stopwatch. Ready, set. That went 0.88, but it crashed into this set. So you can't see it, but I've got this physics set sitting here that I'm going to move. Keep banging into it, and that's not good. Move the obstacles out of the way. As if I even needed to say that, but I did. Okay, let's try that again. And ready, set. Oh, no good. Are you having some issues now and again with your stopwatch? 0.81. Okay, so the time was longer. The time was longer. That means the acceleration was smaller, which is what we sort of expect, don't we? Reset. 0.84. 0.84. Quite a similar time. There's not a lot of difference between 0.81 and 0.84. That's actually, that result is quite reliable. Okay, that's quite a reliable result. The result is quite similar, which I'm really, really happy about. Reset and 0.87. Time seems to be going up just a little bit, but that's okay. All right, let's work out the average. 0.81 plus 0.84 plus 0.87 equals, divided by 3, gives me 0.84, which is good. That's about the value I expect, 0.84. And what's the acceleration? Okay, so it's 2 times 1.1 equals, divided by 0.84 squared equals 3.1. 3.1. Great. Let's pop another 50 ml of water into this bottle. Da, da, da. Perfect. Here we go. So now we're doing 150 grams. That's the bottle plus 100 ml of water. Ready, set, go. 1.16. Now I just noticed something that I'm not overly happy with, but there's not much I can do about it, and that is that there's a bit of sloshing going on. Sloshing's not great. Sloshing's not great. It's not disastrous. Sand would actually probably be a better mass because it wouldn't be sloshing, but that would take a lot more effort and time, which I don't have. Ready, set, go. 1.09. 1.09. Again, that's close value, but not. Yeah, that's okay. That's okay. It's still quite similar. Ready, set, go. 1.04. Okay. All right, let's work out that average. 1.16 plus 1.09 plus 1.04 equals, divided by 3 equals 1.1. Okay, so 1.1. Again, the time has increased. And what's the acceleration? So we've got 2 times 1.1 distance gives me 2.2. Divided by 1.1 squared equals 1.8. 1.8 meters per second. Let's go. 50 more mil. So we've now got a total of 200 grams. Stretch that out to 1.1. Very good. Stopwatch. Reset. Ready, set, go. Boom! 1.4. 1.4 seconds. Stretch him out. Reset. Make sure it's heading in a straight line. Ready, set. 1.43. Good. Set. And 1.22. Now, here's the thing, okay? That's quite different now. That's a whole 0.2 seconds out. I'm going to redo this trial. Okay, I've decided I'm going to redo that particular trial just to see whether that was an outlier. Maybe I didn't press the button at the right time, just because I've got my doubts what happened. 1.32. Okay, I'm going to stick with that. 1.32. All right, let's work out the average. 1.4 plus 1.43 plus 1.32 equals, divide that by 3, gives me 1.38. 1.38, which I'll just call 1.4 seconds. And let's do the acceleration. 2 times 1.1 equals, divided by 1.4 squared equals 1.1. 1.1 meters per second. And now let's do the final value. So now we've got 200 ml of water. Now this bottle will actually take 250 ml. I mean, you probably could do one more value, but I think that might be a bit too much mass for this situation. So that's probably why I'm not doing it. Click. There we go. Great. All right, reset. Ready, set. It says 1.34. Okay, 1.34. The reason I didn't like that was that I had a time of 1.32, but I'm going to write down what I found. That's the best thing for a scientist to do. Write down the results that they get. And reset. And 1.44. And let's do another one. Reset. Just make sure everything's nice and tight and straight. Reset. 1.69. Now that was quite large. That was a long one. So I'm just going to redo that one and just see. Okay, I just want to confirm, double check. Making sure everything's nice and straight. That was 1.4. Let's get an average here. 1.34 plus 1.44 plus 1.4 gives me, divide that by 3, gives me 1.4. Now that is the same as the result above, which is I'm a little bit surprised by. Okay, there's a surprising result. Let's graph this, because when you graph it, you get a much better picture of what's going on. So we can call it Newton's second law. Always do a little title when you do a graph. And what we change, we put on the horizontal. So what we change is the independent variable, that's in grams. We'll start off with 0. Now we went up to 250. So let's go, every second one will go up by 50. So we'll go up by 25. 25 is 50. 75, 100. 150. 200, 250, and let's go the acceleration down here. Meters per second squared, and we've got to go up to 6, which is close enough to 10, so we'll go up by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so for 50 grams, okay, for 50 grams, we will go to 5.9. So I start at 50 and I go up to 5.9, and I put a cross there. 100 grams, it goes to 3.1. 150 grams goes to 1.8. 150 grams goes to 1.8. 200 goes to 1.1. And 250 goes to 1.1. And I'm going to draw a line of best fit. And it's actually a curve that will look like that. And that, my friends, is a beautiful relationship. That tells us that the acceleration is inversely proportional to the mass. And that is that as the mass increases, the acceleration decreases. So as your mass increases, your acceleration decreases. And if I was to extrapolate, this would actually probably keep going up, 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 up like that, get closer and closer to this axis, and this one will go down, 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 and closer to that axis, axis there. So the discussion, clearly, as the mass increases, the acceleration decreased. The times for each trial were quite similar. So generally, the times for the trials were similar. And unexpectedly, my 200 and 250 mil results were actually the same. Unexpectedly, results 200, 250, same. And so that's an area that I'd probably want to do more trials. So the conclusion is, I look at the aim. What's the relationship between the mass of an object and its acceleration? The acceleration is inversely, that means upside down, or the other way, is inversely proportional to the mass, there we go, of the object. Yeah, and you can put if force kept the same, when force is constant. Great. Oh well, hopefully that was a big lesson, wasn't it? Lots of experimentation, trials, that sort of stuff, but the outcome was absolutely fantastic. I wish I actually had this equipment when I was a physics teacher for 25 years. Because in schools they use big dynamic trolleys, lots of weights, it's quite dangerous. It's anyway, this is much better. Okay, alright, looking forward to seeing you again soon, and bye for now. Hey all, welcome to the Year 8 Physics High School course. We're up to Lesson 8, Newton's third law. So in this lesson we're going to be exploring Newton's third law. You'll need a few extras. You need a piece of like hose pipe. Now this one's a clear tube. I think it's like from an aquarium sort of get up, but you could use like just the normal bit of green, hose pipe that you've got in your yard, in your garden. Basically pull off one end, get some scissors and snip off a section, and then put the other end back on. No one's going to notice 10 centimeters of plastic pipe missing, okay? And maybe you might need some tape, but probably not, okay? Probably not. We're going to start by making just a little physics cart powered by a balloon. Okay, physics cart powered by the balloon. And I've still got my cart made up from previous lessons. When you make up your cart, don't forget to put the timber washers. If your wheels are starting to slide off a little bit, just start using, instead of large wheels, you can use the medium wheels or the small wheels, that's okay. And the hose goes, you put the balloon over the hose like that. Now, if that comes off easy, then get a little bit of sticky tape and run around with it. But that one's not going to come off. And what I'm going to do is, I've got the elastic band wrapped around the cart. I'm going to slide that pipe in there like that. Yeah. And then blow up the cart. Or blow up the balloon. Let's go the other way around. Whoop, like that. And what's going to happen if I let it go? Whoa! Whoa, that was like a rocket. In fact, that was a rocket with wheels. What about if I go this way? Yoo! What about if I do a jump? Oh, that would be cool. Will it do a jump? Whoa! Yes! How far can you make your cart jump? Now, don't let it jump off a table, because it's going to hit the ground and smash into pieces. You then will probably have to glue it back together with some PVA craft glue, just the white wood glue, to fix up your cart. But how does this actually work? Well, we've got some energy transformations, of course. We've got elastic potential energy changes into kinetic energy. But how does it cause the cart to go forward? Well, it's not straightforward. I shouldn't say it's straightforward. But it's according to Newton's third law. Now, you might have heard of, for every action there's an equal and opposite reaction. Maybe you've heard that somewhere, somehow, read it, seen it, I don't know. And that's what some people, they recite when they have to recite what Newton's third law is. For every action there's an equal and opposite reaction. It's not bad, But there is a better way to learn it that will help you understand the physics of it. So this is basically how I learn it. It's a little bit trickier, but it goes like this. If object A exerts a force on object B, then object B exerts an equal but opposite force on object A. So let's give that a go. In this regard, object A is the cart, and object B is the air inside the balloon. So object A is actually the cart, the tube, and the balloon, right? So object A is the cart, the tube, and the balloon, and the elastic band. All that is object A. Object B is the air inside the balloon. So object A pushes, the squeezy balloon, pushes the air to the right. Pushes the air that way. Pushes the air backwards. Yeah? So we could say that object A pushes the air that way. Well, object A pushes the air that way, and the air is object B. Therefore, object B, the air, pushes the cart to the left, or forward, or that way. So let's do this again. Object A pushes the air to the right, and object A, and the air is object B, and object B, which is the air, pushes the cart the other way. That's how it works. Would this work out in space? Would this work out in space? Yes. Because if you blow up a balloon out in space, the balloon is object A, the air is object B, the balloon pushes the air that way, and the air pushes the balloon that way. Woo! Forces act in pairs. Let me show you. Take a syringe, use one hand, and open the syringe. Pull open the syringe. You can't pull open the syringe. You need your second hand. The second hand has to grab the barrel of the syringe. Now you can exert a force and pull out the piston. The problem is, if you're trying to pull out the piston with just one hand, you can't actually exert the force. You actually need an object to grab it to exert a force. This hand here is going to exert a force this way so that I can pull the piston out that way. Do you notice that? Forces act in pairs. So this hand pulls to the right and this hand pulls with the same force to the left. Okay, the forces act in pairs. You can't just get an individual force. That's hard to understand. I can't push on nothing. If I want to push on something, I've got to have something there to push on. Now I can push on something because there's something pushing back. Okay, this is quite a difficult concept, and so we're just going to be touching it and getting a feel for it. Okay, we're going to get a feel for it. So let our fingers do the walking. Now, let's have a little look. If I walk with my fingers along this piece of wood, oh yeah, I can pull my fingers forward. You try that. You try walking along the table with your fingers and sort of like have your fingers pull your hand along. Can you do that? Your fingers are pulling your hand along. What's actually happening here? Well, your fingers are pushing the table that way, and the table is pushing your fingers this way. You might say, what are you talking about? Well, in this case, object A is the fingers, and object A is pushing on the table, which is object B, to the right or backwards, and the table is pushing your fingers forward. Now, if you don't believe me, get the cart. Put the cart there and then try. Whoa, see? When I walk with the fingers, I'm pushing back on the cart. Now, the cart can't actually really push my fingers very hard at all with much force, and so my fingers don't actually move. Did you know that we could actually, if every person in the world stood in a long straight line and started walking, we could push the earth backwards. You could actually slow its spin down or speed its spin up, because you're literally pushing the Earth backwards. Now, obviously it is a big concept. Another idea: if you go for a swim in a pool, how is it that you can actually go forward? The only way you can go forward is that if you push the water back. You push the water back and the water pushes you forward. Push the water back and the water pushes you forward. That's what actually causes you to move forward. So Newton's third law: if object A exerts a force on object B, then object B exerts an equal but opposite force on object A. What's another classic example? Well, obviously, if I blow up a balloon and release it, woo, shot out over there. That balloon was the one that I had bicarb soda in. That's why I'm like, that was not a good move at all. The balloon pushed out the air one way and the air pushed the balloon the other way. What about if I push down on the table? Push down on the table. My hand is object A, the table is object B. What does object B do? Object B pushes up on my hand. That's why my hand doesn't go through the table, because there's a force pushing back up on it. If I put the bottle here, what's the forces acting? You might say, oh, weight force is pulling the bottle down, and that is true. Therefore, the bottle is actually pulling up on the table and on the earth. Okay, the bottle is actually pulling up on the earth. Gravity is pulling it down, and the bottle is pulling up the earth. Why don't the two come together? Because there's a solid table that's compressing between the two. You could also just say that the bottle is pushing down on the table and the table is pushing up on the bottle. And that's why it's not accelerating, because one force is acting down on it and another force is acting up on it, and they are balanced forces. I've got a little bit of a poem for you. Imagine there was a ball falling, and imagine that the ball and the earth could speak. And this is the poem. Said the earth, so the earth is talking, said the earth to the ball falling free. Woo! Oh, you're enjoying this falling, I see. Said the ball to the earth with a little surprise, but it's you that is falling, not me. Let me do that again. Said the earth to the ball falling free, so the ball's falling. Oh, you're enjoying this falling, I see. Said the ball to the earth with a little surprise, but it's you that is falling, not me. What is going on here? Yes, the earth is pulling down on the ball and the ball is falling. But the ball is also pulling up on the earth, and so the earth is actually accelerating towards the ball. But why don't we feel the earth accelerating? Because of Newton's second law. Because the earth is so massive, it will have a very small acceleration compared to the acceleration of the ball. Oh, get your head around that lesson, hey? Okay, all right. Hopefully I haven't given you too much of a headache, and I look forward to seeing you again soon. Bye for now. Hey everyone, welcome to lesson 9 of the Year 8 physics course. The lesson is bounce height of a rubber ball on different surfaces. So this surface here is a bamboo table. The table is sitting on a concrete floor. Your surface that you're sitting at might be carpet, or it could be, I don't know, a vinyl floor. Who knows? Could be a timber floor. Could be a cork floor. Unlikely. Although I had a bedroom when I grew up which had a cork floor. Very good for falling out of bed. It didn't hurt very much. But anyway, we're going to do an experiment today. And the experiment is, how does the surface, which a rubber ball, and there's a rubber ball in your sets, how does the surface affect how high the ball bounces to? So we're going to use the scientific method, and again we're going to use my lotus flower experimental design system, because in the very center we've got the independent variable, And that's what we're choosing to change each time. And we're going to be dropping the ball onto concrete. We're going to drop the ball onto timber. We're going to drop the ball onto carpet. And we're going to drop the ball onto a piece of hard foam rubber. So I'll call it foam rubber. So that's what we're going to change. What are we going to measure? Well, we're going to measure how high the ball bounces to. That's our dependent variable. And the dependent variable depends on the independent variable. So the dependent variable, the height that it bounces to, will depend on the surface on which we drop the ball. And so that's the height the ball bounces to. Now, we then have to keep all the other variables the same. We have to control all the other variables. And so what are the other variables? Well, we have to use the same ball each time. A solid rubber ball. It would be silly, wouldn't it, if we changed the ball with every different surface. Then we wouldn't know, if we use the rubber ball on one surface and then the foam ball on the other surface, that's just ridiculous because we wouldn't know what caused the change, whether it was the foam, whether it was the surface or the ball, the type of ball. So, the ball material, the ball diameter, we should use the same size ball each time. Room temperature. We should do this experiment in the same room, really at around about the same time. We shouldn't do one activity in the morning when it's cold and the particles of the ball are moving slowly, and so it's a little bit more rigid, and then come back, have a break, come back 5 hours later. That's a long break, isn't it? When the room is hot and the ball is now, the particles are moving faster, it's expanded, it's got different properties. No, we need to make sure that we have the same room temperature. And I'm going to guess that this temperature in this room is about 22 degrees Celsius. The temperature of the ball. Well, you shouldn't put it in the fridge and then do it and then put it in the freezer or put it in hot water. No, that could be a different experiment. That experiment could be, how does the temperature of the ball affect the bounce height? Now, I wonder whether that's an experiment that I've actually thought about, because that would be a good one. No, you're saying, no, Jacob, no more experiments. No, it's okay. It's all right. The temperature of the ball, we're going to do room temperature, which is just 22 degrees Celsius. I shouldn't be holding it like this between experiments because my body temperature will warm it up. So I'll put the ball down to let it adapt to the room temperature. The ball release height, now that's important. We need to release it from 1 meter every single time. Okay, 1 meter every single time. And the ball released, okay, that's a good question. When we say drop the ball, that's different to throw the ball. Dropping the ball implies that we release the ball and that its starting velocity is 0. That's what the word dropping means. Dropping means we're actually saying that it starts at rest, a velocity of 0. You could say drop or release, but drop is perfectly fine. Can you think of any other variables that you need to control? I've left space for 2 more. Maybe you can think of, should we have the same light? Would light affect it? Well, that's scraping the barrel, isn't it? The same person, yes. Well, if you're releasing it from the same height. The same planet. This morning I'm going to do it on Earth, and in the afternoon I'm going to do it on Mars. Yeah, well, that's kind of obvious, isn't it? Okay, all right. Well, before this lesson started, I made a little bit of a piece of equipment, and I've just got a scrap piece of timber. Now, you don't have to have this, but it will make it a lot easier. You could even use a broomstick. And what I've done is I've taped the measuring tape to the piece of wood. Now, just look here carefully. Notice that the let me just fold this out a little bit. Notice that the 0 of the tape measure is not at the end. The 0 is actually here, which is about 2 centimetres in. Some people forget about that and they end up with a 2 centimetre 0 error. Whenever you're using a measuring device, just check where the actual 0 is. Don't always assume it's at the end. And then what I've done is I've taped it to the 100 centimetre mark there. I've taped the tape on, and then just with the texture drawn 90, 80, 70, 60, just so that it's very, very clear. We're going to do the experiment down there, and we're going to use a bit of technology to help work out how high the ball bounces. I'm actually going to film it with my iPhone. You can film your experiment with a mobile phone or a video camera, because that means later on you can review the footage and make a better decision about how high the ball bounced to, rather than just trying to guess it with your eyes, and you'll see the ball going up and going, I think it's gone to there or there. If you use some video footage, you can review it and get a much more accurate value. Okay? And so we're going to be doing this on a few different surfaces. I'm going to do 1, 2, 3, 4 surfaces. 1, 2, 3, 4. There's actually a 5th surface there that you could do it on. I don't know, artificial grass, ice. You have to make a big ice cube. It could be asphalt, the driveway or something like that. And we're going to bounce it, do the experiment 3 times. We're going to do 3 trials for each surface to find the average. Okay, so without further ado, let's go collect our data, and then we will collect our data. That means doing the actual experiment, and then we'll review the footage and get our heights. Okay, let's go. Okay, so I've got my piece of wood with the tape attached. I'll put it up against the wall as vertical as possible. And our first thing we're going to try is the concrete. The first surface that we're going to try is the concrete. And I think it will bounce fairly high. So I take the ball and I hold it at the 100 centimetre mark. I'll just bring it out a little bit and I'll drop. Ready, set, drop. Whoop. And I'm going to actually replay the video to see what height it went to. So let's do the next attempt. Number 2. There we go. And let's do number 3. All right, so I'm hoping I'll be able to get the 3 heights from that. Let's do another surface. Let's try some piece of timber. So I'll put the timber there and I'll put the meter rule on top of the timber so that we've got the correct height. All right, what will happen? Let's find out. And drop. Number 1. Number 2. Number 3. Let's now do carpet. I've got a piece of carpet. There we go. What's your prediction? I think it won't bounce nearly as high. 100. Oh! Oh! 2. And number 3. All right. And for the final one, let's do the foam. Okay. All right. So bringing in the foam. This is a piece of foam that we use to make our foam inserts. I'm going to pop that there. And here we go. 100 centimeters. Whoa. Whoa. And number 3. All right. Let's go analyze these results. Okay, so let's analyze these results. Now, I've got my iMac in front of me, my MacBook, because I put the video recording of the dropping the ball onto here, and I'm running QuickTime and I'm recording the screen, which will allow you to see this this video to help so that you can see how I'm going to analyze the heights. So our first surface was concrete. Let's write that in. And the first bounce height is, if I press play and drop the ball, I'll just turn the sound off. And there we go. I'm about to drop it. And drop. I press space bar to pause it. And now I'm going to use my right hand, and you can see my right button, and you can see the motion of the ball. It's going up, 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 and it's almost come to a maximum there. There we go. It's gone past the maximum, so I'll just go back to the maximum, which is right there. Now, I wish I'd drawn some better marks with the text, but I can see it's at about 74. It's about 74 centimeters, so I'll put 74. Okay, play that. That was the first one. And then I'm talking a bit. What am I talking about? I'm not too sure. But here we go. I'm about to drop it for the second time. And it drops. And this time, whoa! It's nowhere near. It hasn't dropped down. And so it's very hard to record it. And so I'm actually not going to record a value there. I'm just going to put a dash. All right. Let's play it again. Here we go. And so that's the second one, and here comes the third one, and pause. Up it goes, up, 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 up. Oh, how far did it go this time? It went up to, I think, 76 centimeters. Now, I don't have to go and test and get a third one. Those two values, it's good enough to use those as it is, and I know that the average is, if I add up those two numbers and divide by 2, I'm going to get 75. So the average is 75. Right, what was the next flooring that I used? Piece of wood. So I'm fast forwarding to the piece of wood. And there we go, I dropped it. And so we've got, it's a piece of timber actually. If we're going to be specific, a piece of timber. Press play. Whoop, and up it goes. How high has it gone this time? Alright, there we go. So what are we at? We're at 100, 90, 80. Okay, I think it's probably gone to 73. Alright, so 73 centimeters. And drop it again the second time. And up, 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 up. Oh, that one again has drifted off, so I'm not going to record that value. Let's see what happens. Hopefully we get the third one. Hey, this one looks a bit better. Although it has drifted to the left a little bit. But you know what? I'm going to put my pen across. And I'm going to call it 75. Well, the average of 73 and 75 is right in the middle. 74. So the timber surface is not quite as bouncy as the concrete surface, although it is very close. Let's fast forward it now to the carpet. Okay, so carpet, let's put this here, and let's see what happens. Boop. Oh, This one's interesting. It only goes up to that height there, and that is actually a little bit difficult for me to see. Ooh, I think it's right on 10, 20, 30, 40. It's right on 40 centimetres. Right on 40 centimetres. Boom, boom. It's a very inelastic collision. Whoa! Go back a bit. Again. Oh, it's gone up a little bit higher than 40. It's gone to 42. And let's press play. Oh, it's ball's running away. And the third time. Whoop. Oh. Go back. Running back. There we go. Oh, wow, that didn't go up. That only went 10, 20, 30. That one was a lot less. That was a real outlier. 10, 20, 30. Yes, it's only gone up to 30 centimetres. That is very strange. I'm just going to grab my calculator. I'm very surprised by that. Okay, so let's just work out the average here. 40 plus 42 plus 30. Divide that by 3. Gives me 37.3. I'm just going to call it 37 centimetres. Interesting. This 30 value is what I'd call an outlier. And normally I would probably discard it, but it is quite significant. It's quite interesting. Really what I should do now is go test carpet again a couple or more times. That's what I really should do, but I'm not. Okay, the next one is the foam, which is sort of a foam, sort of a rubber. And here we go. I'm about to change it. Let's fast forward it. Put down the rubber. Very good. And drop the ball. Whoop. And let's see how high it goes on the rubber. 10, 20, 30, 38. 38. Trial 2. Oh, let me fix that up. And 10, 20, 30. Oh! 32. Tops. Again, quite different. So, not what we'd call reliable. 10, 20. Whoa! What? 10, 20. Again, only to 22. Interestingly, the third time, I think that's just coincidence. It's not like third time's unlucky or something like that. 38 plus 32 plus 22 divided by 3 gives me 31. 30.66 is 31. So let's graph these results. And this is ball bounce height. So I always have a title, something about that describes the experiment. What we put on the horizontal is the independent variable. So in this case, it's the surface. And what we put on the vertical is the independent variable. No, it's not. What we put on the vertical is the dependent variable. Hopefully I've said this okay. The surface, what we chose to change, is the independent variable. What we measured and what it depended on the independent variable is the actual height. Sorry for any confusion there. And it's in centimetres. Now this is not going to be a line graph like we're used to, and that is because there's no relationship between the different surfaces. So for our first surface, concrete, we've got 4 surfaces. So I'm just going to actually it's going to be like a column graph. So this is going to be the concrete. So we'll go concrete there. Timber is going to be here. Timber. Carpet. Haven't planned out this very well, have I? Carpet and foam here. And our maximum height was 75. We started the ball height dropped from 100. So in actual fact, I'm actually going to just go up by 10s. You always go up by the same interval each time. I can't write, so I'm writing 60 here. I can't write 80 here. Oh, I just wrote 80. What an idiot. Okay, 70, 80, 90, 100. That's good. And so our concrete, the average was 75. So I go up to 75, which is here. I draw a line across. And then I can do some stripes so that you can quite clearly see how high the ball bounced to. Timber, 74, so a little bit less. Very, very close. I didn't actually think it would be as close, to be honest. The carpet, though, kaboom. Wow, that carpet really does absorb a lot of that kinetic energy. And the foam also absorbs a lot of the kinetic energy. Perfect, and we can quite easily see that the concrete is the bounciest surface that we tested, and the foam is the least bouncy. So what we can clearly say is that the surface affects, is it affects or affects? Affects, I'll try. Affects bounce height. Concrete, it's the hardest surface. Has the highest. And the foam, which is the softest and the springiest, has the least. This is where we can suggest an improvement. Suggest more trials. Suggest at least 5 trials. Oh, that's where I've got suggested improvements down here. Suggest at least 5 trials. There we go. Let's pop them there. Suggest at least 5 trials. Also, there was times that I could hardly read I couldn't see the line very well. So really I should have put clearer lines. Use clearer lines on the wooden timber. But it was a good way of judging the height by filming it, that's for sure, to see values more clearly. But it's definitely a good way of doing it, because you could go backwards and forwards and double check. Conclusion, concrete, timber, carpet, foam is the order of most, and in quotation marks I'm going to put bouncy surfaces. There we go, we've actually put them in order. Well, there we go, that was a great experiment, wasn't it? Planning, designing the experiment, determining what's the independent variable, the dependent variable, what are the variables to control, carrying out a relatively fair experiment. Filming it was great, but I should have done more trials. Graphing it so that you can clearly see the relationships, looking at those relationships and having a bit of a discussion, coming up with suggested improvements, and then answering the aim by, it says, how does the surface which a rubber ball is dropped onto affect its bounce height? Well, the concrete, the timber, the carpet and the foam all affect it in varying amounts. Anyway, there we go. Thanks for joining me today. Look forward to seeing you again soon. Bye for now. Hey everyone, welcome to lesson 10 of the year 8 high school physics course. We're going to be looking at the speed, how fast a wave travels, a compression wave travels in the Slinky spring. Now, you're going to need for this lesson, one, a helper. Now, I don't have a helper, so my helper is going to be like this long piece of timber, and I've screwed the end of I put some screws in the end of the timber and I've attached the spring to the end. You'll need someone probably to hold it, and you'll also need a stopwatch. Now, I'm filming with my mobile phone, so I'm going to use just a regular old stopwatch. You also need out of your set the tape measure and of course the spring. So what are we talking about? Well, we're talking about that if I extend this spring to 1 meter and then release a few rungs, you can actually see the wave travel down and then back up. You might not be able to see it, but I can see it traveling down and back up. And there's a certain amount of tension, pulling force in this spring. And so the question is, what happens if we change the tension? What happens now if I extend it up to 1.6 meters? There's obviously more tension in it. The pulling force is greater. Will that affect how fast the wave travels backwards and forwards? Now, this type of wave is actually what we call a compression wave. And so we could do the speed versus the length of the spring. That would be perfectly good as well. But I've found a way where I can actually work out the tension in the spring. And I used a rubber band, and by pulling on the end of the rubber band, the further I pull the spring, the further the rubber band stretches. Now, I could have used a spring balance to work out the tension in this spring, but the problem was I lent my spring balance to somebody else and I don't have it, so I sort of have to make my own spring balance. And I hung weights on it, and I worked out that for every 30 grams of weight, it would stretch by 1 centimetre. So I was able to work out what the tension was for 1 metre, or 100 centimetres, and the tension was, I lost my data sheet. Got it. And the tension was 0.6 newtons. 0.6 newtons of tension for 100 centimetres. 0.78 newtons for 120, and so on, but we'll be recording that. So let's have a little look. We've got a compression wave travelling in the Slinky. It's going to travel down, it's going to reflect, and it's going to come back. And we're going to time how long it takes to go down and come back. That's going to be the time. And so the distance it travels is twice the length. And the independent variable, what we're changing, we're going to be changing the tension. And we're going to do that by changing the length. What's the dependent variable? The speed at which the wave travels, the time it takes to go down and come back. That will depend, I think, on the tension. I think the tension will affect it, but that's what this experiment is all about. So with the help of a second person, tie the Slinky onto lay it onto a smooth surface. Has to be on a smooth surface so that it's free to move. If you put it on carpet, the wave won't travel, okay? And stretch it out 1 metre using a stopwatch, or film it in slow motion, okay? Using a stopwatch or film it in slow motion. Work out the time it takes for the compression wave to travel down and then back, okay? And then repeat again so that you have 2 trials. Now, ideally you'd want 3 trials, but I ran out of room on this sheet, so I couldn't do 3 trials. Find the average time for each, and then calculate the speed of the wave by using the formula speed equals distance over time. So, without further ado, we're going to get into it. I'm going to need my stopwatch, and I'll reset it, and I'll hold that there like that, and I'll be like, I know what I need to do. I need to hold this spring in place, and I'll use that weight. There we go. Hey, look, Mum, no hands. And that way I can, there we go, perfect. Okay, here we go, ready, set. Oh, that didn't travel very far enough along. Actually, have to make sure it travels. 0.59 seconds. So our first tension is 0.6. Our first distance is down and back, so 100 times 2, which is 200 centimetres. Now I'm going to actually change that to metres. So I'm going to change that to metres, and I'm going to put 2 metres in. And my first time was 0.59. And let's do my second time. 0.62. Okay, those two values are remarkably similar to each other. And to find the average, we add the two numbers together. 0.59 plus 0.62 equals 1.21 divided by 2 gives me 0.61. So 0.61. And the speed is the distance it travels, 2 metres divided by 0.61 equals 3.28, which is close enough to 3.3. All right, so let's go 3.3. All right, good. Next, let's now stretch it to 120 and reset. 0.65. All right, so what is the tension? The tension is 0.78. 0.78. The distance it travels, it's 120 centimetres times 2, so 240. So that's 2.4 metres. It's just travelled 2.4 metres, and in 0.65 seconds. 0.65. A little bit longer, but don't forget it's travelled further. And I don't think I started that very well then. 0.59. Alright, so let's get the average. 0.65 plus 0.59 equals, divide that by 2, gives me 0.62. Slightly longer, but don't forget it's travelled further. So the distance is 2.4 divided by 0.62 equals 3.9, 3.87, which is 3.9, and I'll pop that in there. Good. Our next tension is 0.96. 0.96 is very close to 1 Newton, which is about the weight of a 100 gram apple. And it's going to travel, I've stretched to 140, so it will travel 280 centimetres, which is 2.8. Ready to roll. And 0.69. Let's go again. 0.60. Well, that's a fairly significant difference. I would like to do more trials, but I don't have the space. 0.69 plus 0.60 equals, divided by 2 gives me 0.65. 0.65. It's travelled 2.8 metres, so the distance is 2.8 divided by 0.65 equals 4.3. Okay, so the speed is definitely increasing. All right, our next value is 160 centimetres, and that spring tension is 1.14. 1.14. It's going to travel 160 times 2, so 320, so 3.2 meters. And reset. And here we go. Ready, set, 0.62. Now, in actual fact, I can actually send this down this way, so I don't have to move too much. Very good. And let's grab this one. And ready, set, 0.53. I think I accidentally stopped it a bit early then. I was anticipating a particular... It's very... 0.60. It's very, very close to my my reaction time. So this the problem is the time. There is a problem with this experiment. The time is too short. I'd love it to go backwards and forwards 4 times, but the energy is transformed into sound and heat, so it's losing too much energy to other ways, and so it's not travelling all 4 distances. So we will see how we go. The average of 0.62 and 0.60 is the value in between, which is 0.61, and the speed is 3.2 divided by 0.61 gives me 5.2. And 180 centimeters, the tension is 1.32, and the distance traveled is 3.6 meters. Okay, so let's stretch this out a bit more. Oh, came off the block of tape that I've got it holding there. Get back on. Beautiful. And ready, set, 0.66. Oh, 0.66. That will make it easier to work out the average. The average is 0.66. It's travelled 3.6 metres divided by 0.66 gives me 5.45. I'll call that 5.5. So we're definitely trending upwards. And our final value is 2 metres. So we've got a tension of 1.5 and a distance travelled of 4 metres. And ready, set, 0.63. It's amazing that the times don't seem to be changing. And ready, set, 0.69. But the distances are changing, of course. 0.63 plus 0.69 equals divided by 2 gives me 0.66. The distance is 4. 4 divided by 0.66 equals 6.1. 6.1. Okay. 6.1. Well, this looks like we might have a fantastic... we've got a great set of values here. And so let's now do the graph. Let's pop this graph and say it's the speed versus tension. And so the tension is our independent variable. So we put that on our horizontal, put the units, newtons. Start at 0, and we're going to go up by 0.2s. So 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. And our speed, our maximum speed is 6.1. So we're going to go up by 1s. 1, 2, 3, 4, 5, 6, 7. We always try and use up most of the graph, and that's the speed, which is our dependent variable, which goes on the vertical, meters per second. So our first value is with a tension of 0.6, a speed of 3.3, so up we go. Lovely, put a nice clear cross there. Next value is a tension of 0.78, which is just under 0.8, and a speed of 3.9. Okay, 3.9 is just about there. And then our next tension is 0.96, which is just under 1, and our speed is 4.3, which is about there. Then we got a tension of 1.14, which is about here, and 1.14, and it's 5.2, so it's about there. The next one is 1.32, which is about here, 1.32, and 5.5, which is about here. And then we've got tension of 1.5, which is here in the middle, and 6.1. Wow, let me just grab a ruler and let's do a line of best fit. Now, at zero tension, it's going to have zero speed. I think, you know, well, I'm just going to plot the graph like that. But if I was to now extrapolate it, now what that says is that the speed is directly proportional to the tension. This is actually staggering how good a relationship it is. But I suspect it's going, I suspect it would do something like that. Because at zero tension, I don't think the wave can actually travel if there's zero tension. But I better put a question mark there because I'm not too sure. But clearly, as the tension increased, the speed increased. The times were very short. The times were very short, which introduced reaction time issues. Okay, reaction time issues. How could we improve this? We could improve this by, I could improve this by filming and replaying in slow motion to get the time. To get more accurate time. And also think if I used a smoother surface, it would be better. Smoother surface to reduce friction. Conclusion? Well, the speed is directly proportional in the zone that we did to the tension. The speed is directly proportional to tension. That means if I double the tension, I'll double the speed. If I triple the tension, I'll triple the speed. Well, that's it for that lesson. That's a very good lesson in terms of the scientific method and scientific skills. And thank you for joining me, and I look forward to seeing you again soon. Bye for now, everybody. Bye-bye. Hey everyone, welcome to lesson 11. the angle of fidget spinner and the length of time it spins. So this is the Year 8 High School Physics course, and my name's Jacob Strickling. I'll be your teacher today, and we're going to be doing an experiment. And the aim of the experiment is to determine the best angle to hold the fidget spinner at so that it spins the longest. Do you think it might spin the longest if you hold it flat, 0 degrees? Do you think it might spin the longest if you hold it at 45 degrees? Do you think it might spin the longest if you hold it perpendicular or 90 degrees to the table? So your hypothesis is your best scientific guess based on your current scientific knowledge, and it doesn't matter whether your hypothesis is going to be proved correct or incorrect. What is important is that it can be tested. We need to have a hypothesis which is testable. And so the method is relatively straightforward, actually. This is one of the easier experiments. Woohoo! They say, thought you were treating us like university students, some of those past lessons that we've been doing. Anyway, hold the fidget spinner at 0 degrees, give it a spin, and time how long it goes for. Okay? Then we record that, and then we repeat so that we have 2 results, and then we can do it at 15 degrees, 30, 45, 60, 75, and 90 degrees. And how are we going to measure those angles? Well, we can actually use our hand like this. The thumb is straight up, perpendicular. The pinky is horizontal. The ring finger is basically 30 degrees. The middle finger is 45 degrees. This index finger is 60 degrees, and this one here is 90 degrees. Now, you're probably going to need help for this one. I'm going to somehow have to grow a third hand so that I can actually hold the stopwatch and the fidget spinner and spin it. So I'm not too sure what I'm going to do, but don't you worry about that. You're going to have help. And of course, in the planning of this, again, I like to use my lotus flower planning system. And very, very important is the independent variable in the center. What is it that we're going to change? Well, we're going to be changing the angle. So we change the angle. And I like to actually write down what the angles are that we're going to test. So this is a really good way to plan a practical. Then the dependent variable is what depends on the independent variable, and that's the length of time of spin. Okay, we'll call it the spin time in seconds. And then, of course, we've got to keep everything else the same. So, of course, we're going to use the same fidget spinner. That will be the very important variable. Same fidget spinner. We have to start it off the same time each time. Okay, so the initial, that's the starting speed. We should do it in the same laboratory conditions. Same lab conditions. But because this is such a simple experiment, I don't think there's a lot of other variables to actually control. So if you can think of some, you can put them in, but I think that's good enough for me now. I'm going to hold it at 0 degrees, give it one big spin, and then set my stopwatch up. Ready, set, go! And I'll just pop my stopwatch here. And I'm holding it at 0 degrees, flat. How long will it spin for? Now, don't forget, you're expected to be doing this experiment yourself, not just watching me. Anybody can watch me. All right, we're at 21, 22, still going, 23, 24, 25, 26, 28, still going. It's going a bit longer than I thought it would be. 40. Whew. It's like watching grass grow, isn't it? Now and again it just touches my skin, which is not good. That is not good at all. 55, 56, 57. Still spinning. And 109. So 1 minute and 9. So that's 70 seconds. Now, I am not going to do the second time or work out the average. We've done enough lessons now where you can work out the average yourself. I'm not going to do it. So I'm just going to call that 70. All right. And 15 degrees is in between the 0 and the 30. Oh, that wasn't hard enough. So remember, it's very important to try and do the same spin each time. That's the hardest part, doing the same spin each time. The same initial speed. And also making sure it doesn't touch your skin. It would be best to make like some type of holder to actually hold the fidget spinner. I've actually done that in the past. I've actually made this device. I might have a look later on and see if I've actually got it still. But it's actually got like, how many? It's got like 7 fidget spinners all at different angles. Okay, so we're at 54 seconds. Interesting. Now again, I'm not going to do the second time, so my average is just going to be the same. Now I'm going to go to 30 degrees. Okay, 30 degrees. No, I could just feel it touching my skin there. Alright, so it's now 30 degrees. The hand is good, but it's not perfect, yeah? So the angles are not absolutely perfect. Keep that in mind, okay? I feel pretty good about that. That angle's actually pretty close. The last one was 54 seconds. It feels like it's slowing down. It is. 45. People, we've got some type of trend happening at the moment. Interesting. The next one is 45 degrees. Okay, 45 degrees. Oh, didn't get to the stopwatch fast enough. There we go. All right, 45 degrees. I wonder whether this trend will continue or whether the time will start increasing now. This is what experimentation is all about. Why is there a difference? Well, there's these tiny little round balls in there. That's why it's called ball bearing. And maybe at different angles they don't sit properly. They're rubbing at certain things. Oh, well, look at that. 30, 41 seconds. It's quite clear. It's quite clear that there is a difference. What's next? 60 degrees. Okay, there's about 60 degrees. And the difference I believe, is definitely due to the angle. It's not due to my starting speed. I think I've got my starting speed pretty good. I think my starting speed is pretty similar each time. I'm not boasting here. I'm just stating a fact. I'm feeling like I'm getting a pretty similar starting speed. I could be wrong. That would be difficult to test, whether the starting speed is the same. And 33. I'll be honest, I'm quite surprised at these results. Okay, I am quite surprised at these results. I'm surprised at the consistent way that they're dropping. 75 degrees. And you might be saying to yourself, oh, well, Jacob's taking a fair bit of time to go from the spin to the time, but it's the same sort of time each time. And it's also I'm doing it fairly quickly, like within probably 2 seconds. And that's 2 seconds over like 33 seconds. So it's not a huge error. And in fact, because I'm doing it the same for each one, that sort of negates the error. 20, 30. And 30. There's one other thing that we haven't actually talked about though. Maybe the ball bearings are heating up. So every time I spin it, they heat up a bit more, they expand, they produce more friction. And so maybe the fidget spinner is changing each time. So in actual fact, I probably should have maybe wait 1 minute between each trial. Okay? So how the control variable is same temp ball bearings. And to achieve that, you'd have to have it sitting there at rest. Yeah? So, all right. Okay, next one. Final one. 90 degrees. Fantastic. I'm actually quite excited by what's happening here. Oh, I hear a rattle. And 22 seconds. 22 seconds. All right. So here I'm just going to go did not do. But you're expected to do it. All right, let's graph this. Fidget spinner spin time. The angle, 15, 30, 45, 60, 75, 90. Notice that there's equal distance for each interval. Similarly here, 0, 50, 100, 150, 200. Time of spin. Okay, I think we can adjust this because it's important to try and try to use up most of the graph. So I'm actually going to change that to, I'm going to call that value there 50 and that value there 100. That way I'll use up most of my graph. Let's start with angle of 0 and the time was 70. So 75 is in between 50, so I'm going to put a cross there. 15 degrees was 54 seconds, so 15 degrees, 54, so if that value there is 75, 62 and a half, 54 is about there. 30 degrees, it's 45. 30 degrees is 45, which is, that's 25. We're going to be about here. 45 is 41. So that's 25 there. So 25, 41, we're talking about here. 60 degrees is 33. It's going to be about here. 75 is 30, which is about here. And 90 is 22, which is going to be about here. It could either be a bit of a curve, or it could be a line of best fit like that. Not sure. That's why I really love the clear ruler, because you can see through it. You can see the point. I'm going to go like that. I'm going to draw a line of best fit. There we go. If that value here was up here a little bit, then I'd probably have done a curve. Okay. But there we go. I've made the decision now. There is a very clear trend. Okay. Clearly, the spin time depends on the angle. In future, wait 1 minute between spins for bearings to cool. Okay, so that we can return it to the initial conditions. The conclusion, as the angle increases, the time of spin decreases. Spin time is inversely, upside down, inversely proportional to angle. There we go. Now that is a solid experiment with some very interesting results. Whether the curve goes like that or straight would need to do some further investigation. We'd probably have to do a better setup in terms of holding this at more consistent or more accurate angles, and even working out a way to spin it at the same speed. There's a lot of potential and scope to turn this into a really deep and proper investigation. We don't have the time here, but we've got enough data to show us that this is worthy of further investigation. Because it's also got some real world practical implications, that ball bearings are used everywhere. Okay, ball bearings are used everywhere, in shafts and skateboards, in cars, in boats, in planes, and maybe it's that they need a redesign so that they are optimum at all angles. You might be surprised. Not everything in the world has been solved, and there's definitely room for improvement. So anyway, well, thanks for joining me today, and I look forward to seeing you again soon. Bye for now, everybody. Bye-bye. Oh, I found the machine I was talking about. Look at that. 0, 10, 20, what's that, 30, 40, 50, 60, 70, 80, 90 degrees. Very difficult to get identical fidget spinners, and very difficult to spin them all at the same time. But you get the idea. The things I've done for science in the past boggles the mind. Okay, bye-bye. Pew! Oh, I love paper cup toy flyers. So welcome to lesson 12, toy cup flyers of the year 8 high school physics course. I'll be your teacher, and we're going to be investigating toy cup flyers in this lesson. So what is a toy cup flyer? Well, you need some cups. Now, don't use glass cups or ceramic cups. You need to use either like cardboard, paper, foam, plastic, things that won't break, and they need to be lightweight. So for this lesson, you're going to need a range of different size cups because we're going to investigate how size and material affects the distance or the time in air. Now, when I say we, I really mean you, because I'm not going to be doing all these experiments. You are going to do all the experiments. I'm just going to help you and describe how to do it. Does that make sense? I hope so. You're probably thinking, what? Hey, are we paying you to do it? Well, no. You're paying me to have written the worksheets so that you can do it. Yeah? All right. So I've been holding your hand quite a lot for the last 11 lessons. So now it's time for you to be a little bit more independent, so to speak. Okay? Oh, I'm an independent variable. Yes, you are. Okay. All right. Now, how do we make these cups? Well, you're also going to need some form of tape. Now, this is some blue masking tape, electrical tape. You could probably do it even with the old clear paper tape. So you can almost use any tape at all. So isn't that good? How do you make them? Well, they're so easy to make. You basically put them end to end, stack them up like that. And then you have to run enough tape around so that they are firmly stuck together. All right? That's the idea. You don't need heaps and heaps and heaps and heaps, okay? I mean, paper tape, it doesn't grow on trees, does it? Maybe it does. Okay. So, there we go. I've just talked. Hey, I've made my own a toy cup flyer. Okay, so then you need to power it. You need to get it spinning. Well, you could probably even throw it with your... Well, I've never tried it before, but I bet you could even throw it with your fingers. I wonder. Ha! Never tried it. It actually... Whoa! It actually does something. But we use an elastic band to get it going. Now, you can use if you've got a big black one in the set, I think there's some big black elastic bands. There could be 2 big orange ones, depending on when you bought the set from us. If you can't find those because they're broken or used up or whatever, you can actually use smaller rubber bands. And what you do with the smaller rubber bands is that you can join them together. Now, to join them together, you sort of cross them over, and then you push one half through the little loop, and then you pull it, right? Now, it's a bit hard to describe exactly how to do it. You cross it over, push one part through, pull it through, and then you've got it. So now I've got a giant elastic band. But here's the trick. This is where it's quite challenging to do. This is where most people can't do it. But you get your right hand, say, hello, I'm the right hand. Okay, and your thumb's very important. And so you pick up the paper cup with your right hand with the thumb underneath. Okay, the thumb underneath, see that? And then you hold the rubber band. Okay, I'll do it with the orange ones because you can see them a little bit better. If I did it with the black one, you can't see that. So you dangle. You're dangling the rubber band, okay, by your thumb. See, it's between your thumb and the tape, right in the center of the 2 cups. Dangle, dangle, dangle. Then you grab the other end with your other hand and you apply some tension. Some tension. Not like as much as you possibly can, but like some tension. These 3 bands have stretched out to about 40 centimetres or so. When you've got some tension on and you're holding it with your thumb, you go around applying the same tension the whole time. So I can actually go around a few times. Then, to launch it, the rubber band must be on the bottom still. Okay, the rubber band must be on the bottom, and I've got it in my left thumb, and I'm holding the bottom of the cup with my right thumb. Then, I'm going to head over here, and there we go, you can see me on that other camera, I believe. And then you release. Oh! Did you see that? What a floater! How awesome was that? Oh, I love it. I love it. I love it. I love it. Let's just try a different one. So, 2 plastic cups. I might even try clear plastic tape. Clear, colourless plastic tape. Let's see if this works. These are so easy to do. Yay! It's not quite as pretty as the other one because there's no stretchiness in this tape, whereas the masking tape had a little bit of stretchiness, but it's not too bad. I might even just strengthen it up with a little bit more. Oop, it got stuck. Woo, timber. And around we go. Where we stop, nobody knows. Okay, so here we go. I'm going to use the black one this time. No, too hard to see. Use the orange one. Right hand, right thumb. Hold the elastic band at the bottom, like that, okay? Then apply some tension to maybe make it about 40 centimetres and then go around. Don't do it too tight. And do it over itself, and that will hold it in place. Then I'm holding the cup, my thumb's on the bottom, my other thumb's on the bottom, the elastic band's on the bottom. Everything's on the bottom, apart from the finger on the top. Then, coming over here, hello everybody. Will it work? Ready, set. Oh, very, very good. So you could measure the distance it travels, and you could get someone to actually measure the time that it's in the air. So with this experiment, what is the aim? It says, how does the size of the cups of a toy cup flyer affect the how well it flies? And when we talk about how well it flies, we're talking about distance covered and time in the air. The longer it's in the air, the better it is, the better it flies. How does it actually fly? How does it actually generate what we call lift? Well, when you release it, it spins. It spins, and a high pressure zone is created on the bottom and the low pressure zone is created on the top. And that high pressure zone pushes it up. And that is called the Magnus effect. And on the second page of the lesson, there's a whole page where you can do some research, and it says produce a 1-page handwritten and hand-drawn poster describing and explaining the Magnus effect. So now it's time for you to do some research. Now you can do the experiment first and then the research after, but that's okay. But I want to see handwritten, hand-drawn, to explain to someone how these paper cup toys actually float and fly through the air. So, make the pay cup or the toy cup flyer, yeah, and it says in the results, what's the largest diameter of the cup? Well, the largest diameter is this distance here, okay, the distance across. What's the length of the toy cup flyer, so what's that length there? What's it made from? And distance it travelled, and the time in the air, and you can write down your observations. Now, this is not a straightforward practical, okay? This is almost what we call an open-ended practical, because there's lots of different variables you can investigate. The flight is not straightforward. The flight is not straightforward, and so that also needs to be taken into account. Now, one question is, how do you measure the distance it travels when all you might have is the 1.5 metre tape? Well, I'm going to tell you. So, I'm going to teach you how you can use this tape to measure long distances. This is what you need to do. You need to go to like a hallway or a large room or something like that, or an outdoor deck or something, and you're going to measure a total of 5 metres. Okay, so you need a total of 5 metres. And you put the 2 marks across 5 metres. And how do you get 5 metres? Well, this measuring tape goes up to 1.5 metres, so you can put it down and then move it, and then move it again, and then move it a bit more, so that you've got 2 points 5 metres apart. Okay, 2 points 5 metres apart. Then you're going to practice walking across and go 1, 2, 3, 4, 5. You're going to try and do it in 5 equal strides. Then you'll do it again. 1, 2, 3, 4, 5. You'll do 5. You're trying to get your strides to equal 1 metre. Now, a stride is the distance you travel when 1 foot travels. That's a stride. That's a stride. That's a stride. That's a stride. Now, if you are finding that after 5 strides, you're not at that point, you have to stretch your stride a little bit. You have to stretch out with each of your strides. Now, you have to do this 20, 30, 40 times so that you can get into your head and into your memory and into your muscle memory that to try and get 1 stride equals 5 metres. Now, when I left school, I actually was a landscaper for a year. And I was able to do, I had to go do quotations. I had to measure people's outside verandas and around pools and driveways. I didn't use a tape measure. I had programmed my body to do strides, and I could measure very, very accurately the length of driveways, the width of driveways, the length of gardens. And so we were able to, instead of running with long tapes and tape measures and that, all Jacob had to do was like 1, 2, 3, 4, 5. Oh yeah, that's 12 metres long, 6 metres wide, that sort of stuff. So it's a very good thing to learn how to program your stride into your mind. Do you think you can do it? I'm sure you can. So I'm going to now leave this experiment over to you. Yes, you are now going to do this experiment all by yourself. Are you nervous? I hope so. Because it will be fun and you'll be able to make the toy cups fly, but will you be able to interpret your findings? And will you be able to draw any conclusions? I don't know. We will find out, won't we? And there was one more thing that I wanted to say. That's what I wanted to say. Maybe about 6 or 7 years ago, I made an invention. Yes, I made an invention. And it was about Christmas time, and it was sitting at the Christmas table, and my wife had bought bonbons, party crackers, Christmas crackers, and everyone, they're wrapped up, they're like these tubey things, and everyone holds them like this, and then you go pull, and you pull, and they kapow, and then they got like lame like crowns and lame jokes and lame plastic toys and that sort of stuff. Those Christmas crackers, and they got the toys are pretty rubbishy. And I remember thinking as I was doing it, I looked down at the cardboard tubes and I went, hey, they look a lot like toy cup flyers. And I thought, bingo! I could make Christmas crackers from toy cup flyers. So I started with just a toy cup flyer like this, and then I poked 2 holes through, and I was actually able to poke through 2 party poppers, 1 party popper this side, 1 party popper this side, and they had the strings that would come out. And then I put some elastic bands in there, put a lame joke, and then we wrapped them up with Christmas paper, and then we had the string which was taped to it so that when you pulled it, it would pull the party popper. Anyway, how good were they? They were so good because when you pulled them, there was a big bang. 2 Christmas crackers or party pack poppers cracking, that was the first thing, and streamers came out. And then the guests were like, "Where's my toy? Well, I've got an elastic band, but I want my toy." And then I said, "It's all good. There's your toy. The Christmas cracker is the toy. The party bonbon is the toy." And then the guests, they put their elastic bands together and then they wrap them around, woo, like this. I should show you exactly how to do it again. Hold the cups, dangle the cups, round we go, pull back, woo! That went quite far actually. And it should be from where it hits the ground, not how far it keeps rolling and that sort of stuff. Well, anyway, over to you now. Oh, and by the way, I got on TV with that invention. I think it was the Today Show, Channel 9 Today Show. They said, "Jacob, we've seen your invention. We want you to come and do it." Now, it wasn't a great experience, I can tell you. TV generally is not a great experience. Anyway, but that's another story for another day. But you can actually go to I've got a YouTube channel called Make Science Fun. I'm like some 10-year-old boy. "I've got this YouTube channel, you should go check it out. I've got 4 subscribers." No, actually, I've got more than 4 subscribers, put it that way. And if you put Party Popper or Toy Cup Flyer or Christmas Bonbon or Channel 9 Today Show, it should pop up you should be able to find it in my Make Science Fun YouTube channel. Okay, over and out. Don't forget to press the button and subscribe. Do they even say that still? I don't know. I never said it. I thought that was so lame. I would never say that. But please subscribe. Joking. Subscribe. Okay, all right. See you later, everybody. Bye-bye, bye-bye, bye. Subscribe. Hey, everyone. In this lesson, number 13, we are going to be doing flying throw tubes. In last lesson, we did flying toy cup flyers. This lesson, we're going with the theme of flight because there is a lot of physics in flight. Forces, gravity, motion, lots and lots of physics. What are you going to need? Well, you're going to need some plastic bottles, okay, PET bottles, different sizes, even possibly different types, okay? And you're going to need a sharp pair of scissors, or if you're supervised and you're allowed, a Stanley knife is quite good as well, but you have to be careful, very careful with Stanley knives because they're very, very sharp. So, and also you need some tape. I've got some masking tape here, some electrical tape. It has to sort of be heavy-ish tape though. So this sort of tape, this cellophane tape is probably not that great sellotape. So first I'm going to try and make flying throw tube for you and show you how to fly it. And the part of the bottle that I want is actually the flat part under the label. So I'm actually going to try and get rid of this label. Oh yeah, that label comes off pretty easy. Oh, look at that. Hey, do you know what this is? You know what this is? A Coke bird. Yeah, so, woo, here comes the Coke bird. Oh, look, that's actually pretty good, isn't it? Oh, very relaxing. Lots of physics in the flight of birds as well. So, okay, so I've taken that off the label and now I can see that there's a zone here under the label that's nice and flat, and I'm going to try and cut that zone off and out. So that's why I'm getting my scissors. I might start a little bit further away from it and I'll cut into it. Here we go. I've managed to pierce into the bottle. Almost. Okay. Now I can cut off and then And then I'm going to come and cut closer and closer and closer to the zone that I want, and then I can do it sort of neat. This is actually working fairly well. There we go. I can even trim it up a little bit. Get it to that perfect height. See that? Look at that. I've done one. Now I've got to do the harder part, which is here. And I'm saying it's the more difficult part because I think the plastic's a bit thicker. Because there's, yeah, I think it's a bit thicker and it slides. So this is going to be a bit trickier. Okay, but I've managed to get in there with the scissors. Now I can poke the scissors in. First cut off the end. Right, now I can start trimming. This will be easier to trim now. You might need an adult to do this for you. Okay. Okay, so that is my tube. So there we go, I've got my tube, and should be smooth all around the edges on both sides. A little bit rough on that side, so I might just do one more little bit of trimming. There's a bit of a bump there. Okay, I think I've gotten rid of the bump. Okay, so there's one tube. And this is how we're going to convert it into a throw tube. Sort of want it nice and round. And I get my tape. And what I'm doing is I need to make one end heavy and thick. So I need to go around and around and around with the tape. Okay. How thick? Well, you can always add some more, can't you? So, okay, now when I throw it, the idea is to throw it like a gridiron football. Have you ever seen the Americans when they play football and they throw a football? They put a spin on it. They use their hand and it goes spiraling through the sky. That's how you have to sort of throw this. You have to throw it, and as you throw it, you'll spin it down, see, on the tape with your fingers to get a spinning action going. All right, so let's give this a go. Let's give this a go, see if it works. Come back, and that was terrible. That was disaster. Absolute disaster. There was no spin on it. Let's try that again, shall we? Oh! That was absolutely horrific. Admittedly, I've never been good at sports. What I'm going to try and do is put some more tape on there. Try and weigh it up a bit more. I've actually done these in the past where I've used a really thin metal strip to get a bit of weight into it as well. Okay, let's try that. Let's try this. Oi! That actually had a bit of potential. Okay. Try that again. More forward thrust required. Not enough spin. Hey, this one's peeling off to the right when it works well. So there is definitely potential there. So a question is to determine the optimum dimensions of for the longest flying throw tube flight. So that has one diameter. This is a smaller bottle. And so you'd have to take that outside, or you'd have to take it into a really long hallway with the working out your strides for, and you'd have to try and throw it at the one sort of speed. Notice how I've got like 8 trials for each one. It's because some go strange and funny, and so you need, when there's variation in the distances, the more trials you can have, the better. Okay, the more trials, the better. So I'm after this section here. So I'll just cut off the back section. And then come on in. Like this. Nice. And now attempt to cut off the front section. Again, the plastic's a bit thicker, and this is actually, so I might have to squeeze it a little bit. This is where an adult would be helpful. Adult! Oh, I am the adult. Sorry. I think I've had success. Pop in the scissors. That's good. And now attempt to trim it up. Here it goes. Yeah, good. Nicely done. I think I've done it. That feels pretty good. Okay. Let's try this. And around we go. So this is a smaller diameter. Will it affect the flight distance? I think it will, but we will find out. Sort of probably the one variable to keep controlled is the number of thicknesses of the, so I probably should have counted that. Okay, ready? Let's see. Oh, more success that time. It sort of floated a bit, so I think I should try and get more spin on it. A bit more forward motion on it this time. More spin, more forward motion. Oh! one peeled off to the right as well. Well, you've definitely got the idea of how to make them, how to throw them, and you need to make sure you do lots of trials and record the distance each one travelled in order to get an average. You're then able to complete the line graph and do a discussion and then do a conclusion. So, over to you. Stay safe with the scissors or the Stanley knife, and yeah, knock yourself out. Not what's the word? Not physically knock yourself out, but you know, it means get into it, get busy, and get sciencing, I guess. Okay, all right. So yeah, it'll be very interesting to see how the diameter affects the distance that these flying throw tubes travel. Okay, all right. Thanks for joining me today, and I look forward to seeing you again soon. Bye for now, everybody. Bye-bye. Hey, paper ninja stars, based on the Japanese technique of paper folding called origami. Welcome to lesson 14 of the Year 8 High School Physics course, Paper Ninja Stars. Now, it's amazing how you can go from a floppy piece of paper that has got, you know, no sort of strength in the lateral. Obviously, it's got quite a lot of tensile strength, virtually no compressive strength. But with simple folds, you can change the properties in terms of its strength and structural abilities, which is why origami is so important, because it helps us appreciate and understand and how we can work with different materials, particularly paper, to actually make useful things from them. So, for example, soft fiberglass, which when you add a resin to it, you can make, you know, surfboards and boats and that sort of stuff. Canvas and Kevlar, you can make sails that are ultra strong and can, you know, allow boats to basically fly through the water these days. I love origami because it's also good for following instructions and working carefully. Paper ninja stars are one of my favourite, but so are paper water bombs. You know, you can actually make a paper water bomb from origami. I kid you not. It will hold water. You can throw it and it will splash. I've also seen those little frogs where you sort of press on its tail and it sort of jumps forward. Or ones where, you know, you pull something and the mouth opens of the animal. Paper storks, obviously, which I think you can get the wings flapping. So, yeah, please further investigate origami and see what you can do. It is a terrific thing. But in this lesson, you're going to be making some different size paper ninja stars, and seeing if there's a relationship between the size of them and like how far they fly. So again, it is a good science experiment, and the equipment that you're going to need is some scissors and paper, okay? And I'm just going to be making one ninja star for you. I've got a camera here to record the movements and the folding and that sort of thing. We'll see how we go. I've actually got a computer in front of me. I'm watching a YouTube video while I do it. And so if you don't like, you know, my hairy arms, or if I'm not doing it very clearly, or my nails are dirty and you can't stand it, feel free to go to YouTube and watch a different video on paper ninja stars, and just find one which has a cover that looks something like that, and you might prefer their music. I don't know. I probably won't even have music with mine, maybe something. But without further ado, I suggest we kick into it. And so we start with a yellow piece of paper and let's go. All right, so firstly we fold the corner down to the end, because what we're going to be doing is making a square. Okay, so we're making a square, and I'm just creasing the line quite carefully, like this. Beautiful. And we get our scissors, and we're going to cut along this line as neatly as we can. There we go. This part here we can discard. So now we've got this triangle, and I've also done another one. So you need two. You need two triangles. We'll open one up, open up the other, and we're going to rotate so that I've got the fold line going this way, and this one, the fold line going that way. All right. Then on the blue one, I'm going to fold it in half. Okay, fold it in half and fold the line there. Nice and press it nice and firmly. And then let's do the same on the yellow one. Fold in half and press the line firmly. Wonderful. Then we can open him up and fight the top and fold it to the middle. And then take the bottom and fold it to the middle. Okay, and then bring up the bottom part and bring it to the top. And so we've got this piece here. Now let's do the same on the blue side. Open it up, fold to the middle, and crease that line nice and firmly. Fold him to the middle, and then fold up. Great, now we've got two very similar pieces. Let's take this one and fold to the middle. Fantastic. And we can open him up and take this one and fold him to the middle. Nice crease again, and open him up. Okay, so see how we got this fold line there? That's important to have that fold line there, because that will help us fold up like so and fold along that, and then on this side we can fold down like so. There we go, foldy, foldy, foldy. Nice and firm. Excellent. Now, similarly, notice how we've got the crease line here. So let's fold that up onto that crease line. And then fold this one downwards, and there's a crease line there as well. Terrific. Look at that. All right. Take that one and turn it over. Take that one and turn it over. Okay, then take this on the yellow, the top corner, and fold it in like so. Nice fold. And then the bottom corner, bring that one in and fold it in like so. Oh, I'm starting to see some form of stars happening here. Take this one, corner, fold it in. Take this one, fold it in. Beautiful. Opening them up, look at that. Look at that. Okay, now it's take. Okay, now take this upper part and fold it down. Take that other part and fold it up so that we have this rhombus type shape. Similarly, take that upper part, fold it down, and then take that lower part and fold it like that. Okay, now the hardest part. Here we go. Now for the hardest part, bring that around here like this. Fold this one down and tuck it in like that. Actually tuck it in to there like that. Then bring that one, tuck that in there like that. So we're doing a lot of tucking in basically. Tuck that one in. Tuck that one in there like that. And then tuck this one in like that. Yay! Hey, Paper Ninja Star. Now, towards the end, I was getting a little bit stuck. So, it might be better to find another video to help you if mine was a little bit clear. I personally don't find this sort of thing very easy at all. Now, the size square that we originally made, we know what size square is used to make this size particular ninja star. And now the idea is to go and experiment. The idea is to go find a hallway or something like that and then throw it at maybe 45 degrees at a particular angle and then measure how far it goes and then do that 10 times and record each distance and then find the average. Then make another ninja star. Different size, and you could actually probably do, I've got down here what do we got? We've got to start with, a 10 centimeter by 10 centimeter ninja, the square, 15 centimeter by 15 centimeter, and 20 centimeters by 20 centimeters. Then, of course, you're going to graph the average distance versus the size, the original size of the star, and see if this is actually a valid experiment. Are you getting any type of reliable results? And it will be very interesting to see, is bigger better or is a small Paper Ninja Star better? Who knows? Well, you hopefully will know if you do the experiment. Okay, well, all the best with your Ninja Stars. And yeah, let's find out if there is indeed a relationship between the distance they travel and the size of the star. Okay, well, thanks for joining me this lesson, and hopefully see you again soon. Bye for now. Bye, everybody. Hey everyone, what do you get if you add some sticky tape, straw and paper together? You get a paper loop flyer. Yes, we're doing more flying in this lesson 15, paper loop straw flyers in the Year 8 high school physics course. So this lesson is all about you doing an open-ended investigation into factors which affect the flight of a paper loop flyer. Now, believe it or not, these things are actually very impressive. Let me show you. Woo! Whoa! They are actually quite interesting. So, how do you make a paper loop straw flyer? Well, you need either a plastic straw or probably a paper straw would be absolutely fine. And you need to make a loop for the front. So, if you get a ruler and a pen, I might do one that's 1.5 centimeters wide. So my first paper loop is going to have a width of 1.5 centimeters. So I'll cut that like that, and then get a pair of scissors and cut as straight as I can along that line. And then with a small piece of tape, you want to just join it together. There we go. Perfect. And so I can measure the diameter of that loop, which is, what's that? 6 centimeters. The diameter of the front loop is 6 centimeters. And so I'll just hold it in place with a bit of tape. So I get a bit more tape and hold him in place. This is not, some things are easy. I don't think this is actually easy. I'm actually going to try putting the tape on the straw first and then bringing it up. Oh no! The tape just touched. Now I can't get it off. Ah! Get off! Oh, will I be able to get this tape off? I don't know. Yeah, you know the only thing worse than sticky tape? Super glue. Never touch that stuff. Oh wow, that stuff's an absolute disaster. When I was a kid, I remember I glued my fingers together. I've heard people accidentally put some in their eyes and they glue their eyelids shut. Okay. Yay, I've got the first loop. Woo. Doesn't do much. Now, generally speaking, the rear loop needs to have a larger diameter. So I'm still going to go with the 1.5 centimeters. And this one's going to be a much bigger diameter. Oop. Cutting, cutting, cutting. Here's one I prepared earlier. Well, I didn't prepare one earlier, so we'll have to build this one live. Yep. Very good. Get the tape. Notice I'm putting it flat on the table like that. It's a much bigger loop, isn't it? Run him around. That was not good. Excellent. Oh, now I'm getting pro at this. Ta-da! So this one, the front loop has a diameter of 6 centimeters. The rear loop has a diameter of 8 centimeters. And that's it there. Will it fly? Don't know, let's find out. Will it fly? Let's find out. Come on. Ooh, sort of came back on me. Don't know. Maybe this loop's too big. Maybe it's better if the front loop is much smaller. Maybe the width of the paper makes a big difference. Maybe. Well, this is the whole idea of this lesson. The whole idea of this lesson is to do an open-ended investigation. That's one where I'm not going to tell you exactly what to do. You can explore. Okay, you can explore what happens if you change the sizes, the diameters, the width. What happens if you use slightly thicker card? What about, the length of the straw? How important is that? So you could almost spend a whole lifetime on a project like this, but don't do that. Okay, don't do that. But if you want to do this project well, if you want to do this investigation well, it's probably a good few hours. You will have to dedicate a few hours of your life to this. So it will be interesting to see what you come up with, what you want to share. I'm very, very interested. I personally don't know the ideal dimensions for a paper loop flyer. I'd like to run some workshops, and have in my mind what the final one they should build for the best distance. Maybe you can help me find that, and when you do, you can let me know at Tiny Science Lab. Okay, well, all the best to you and your families with the paper loop straw flyer. Good luck. All the best. Bye for now. Hey! Hello back there. Welcome to lesson 16. The size of wheels and roll distance for the physics cart. This is the Year 8 Physics High School course. I hope that you've been enjoying it so far and learning lots. We're going to be doing an experiment together today, and you're going to have to put on your thinking caps. I'm pointing to my eyes, and then I say thinking cap. Doesn't matter. Okay, so basically what we're doing today is we've got three different size wheels for our physics cart. We've got the large wheels, the medium size wheels, and the small wheels. And we are going to be releasing the cart from the top of, well, not from the top of the ramp, from a mark that I've put on the ramp. And the cart's going to roll a certain distance, and we're going to measure that distance. And the question is, how does the size of the wheels affect how far the car will roll? What do you think? Do you think it will make a difference? We're releasing it from the same height each time. It's a flat surface each time, so maybe it won't make any difference at all. But maybe it will make a difference. Maybe, if you've got a big wheel and you're going a certain speed, the big wheel's not turning as much. And if it's not turning as much, then maybe there's less friction. I don't know. What's your hypothesis? Okay? So essentially, Here I've got a picture of a box of tissues with a ramp. Now, what could you use as a ramp? Well, if you've got a tiny science lab chemistry table, you could use that as a ramp. What about a big book? A big book like that with the tissue paper. The only problem is you've got a bit of a brump. You've got a step. And so you'll need a piece of card or something like that to lay down so that it doesn't have such a big step. We've got a little bit of a step here on my setup here, so I might just put a piece of like blue paper and just get some masking tape and just tape that there like that, and then it's not quite as big a step, and that actually feels quite good, so I'm quite happy about that. You'll also need your tape, okay, your measuring tape, and once it's out, you can just sort of leave it out. And we're doing from the distance from the end of the ramp to how far it rolls. So there's the end of the ramp there, and I might just actually tape that measuring tape in position. There we go. Great. That way it won't move. I've also got a calculator here to measure averages. So, without further ado, we're going to start with it says start with the small wheels. So let's start with the small wheels. So I'm going to put the small wheels on. Make sure that you use your little wooden washers, okay? Because they will help remove any friction. And the first time that these wheels go on, the harder it is to push them on because the hole's quite small. Every time you move these in and off the axles, that hole gets a bit bigger and eventually gets so big that the wheels will fall off. If that's the case, we, Tiny Science Lab, sells spare parts. Okay, so I've got a nice little cart here. I need to put a mark. From where I'm going to release it. So I might actually get a piece of tape. Alright, so I'm going to put a piece of tape like a starting point so that I know where to start it from each time. Now I'm a little bit limited with my distance here, so I can't start it from the top because otherwise the thing might roll off and I don't want that to happen. So I'll put the front wheels on the tape there and then let go, and let's see how far it goes. Okay, so it has travelled to 91 centimetres. So my first trial is 91 centimetres. What's my second trial? Let's see. Alright, 94 centimetres. Now we do hope that these values are going to be similar. Okay, that sort of indicates the reliability of this investigation. If they're hugely different, we'd know we've got a bit of a problem with the setup. So that's 91.5. And I'm going to work out the average straight up. Okay, so I turn the calculator on. I add up the three values, 91 plus 94 plus 91.5 equals, divided by 3, but before I press equals I like to play a little game. I like to estimate what I think the average will be. So it's going to be bigger than, it's going to be around about, I think, 92.5. That's my guess. And the answer is 92.2, which is close enough to 92. And I'm happy with that. All right, let's now put the medium-sized wheels on. Okay. Well, actually, another part of this practical is what happens with 100 ml of water. Oh, forgot about that. What about it with 100 ml of water with 3 centimetre wheels? Let me get 100 ml of water. And I'm going to add it to the cart. And let's see what happens. Same height. Will it go further? I think it will. Oh, kapow! The bottle fell straight off. So let's put it on with an elastic band, because that was not a good start. Okay, there we go. Let's try that. All right. And release from there. Everything set, go. Oh no! It nosedived. That's a problem, isn't it? Okay, I might put it further back on the cart. There we go. I'll put it further back on the cart. Let's see what happens now. I've got a piece of string there. Need to get that string off. Let's try. Let's see what happens now. Yay! Oh, hello. That's quite surprising. It only went to 71 centimetres. Let's try that again. And release. Oh, similar result. 72.5. And thirdly, oh, we are getting some consistent results here. 71. I think the average is going to be about 71.5. Let's find out, shall we? 71 plus 72.5 plus 71 equals, divided by 3, gives me 71.5! Yeah, I'll put that as 72, just to round up. Okay, so now I'm going to put on the middle size wheels. Small wheels are done and dusted. Let's now do the middle size. Done and dusted. Why would something be done and dusted? I don't know. Some sayings you just say, but you don't know the origin of them. Done and dusted. Don't know. Sorry. Okay, the middle wheels. We'll start with the bottle on and then take the bottle off. So we'll go a little bit back to front. That saves a bit of time. Okay, just making sure the wheels are not scrubbing against the thing. That looks good. Let's pop that there. Okay, same height. And action! Oh, went a little bit further. 86 centimetres. Interesting. Let's try this one. Are the results reliable? 87 centimetres. Yes, that's actually quite reliable. And third time. Oh no! It did a head over heels. And action. 87.5. I'm going to guess an average of 86.5. So 86 plus 87 plus 87.5 equals, divided by 3 gives me 86 point. I think that's a 0. We'll go to 86. No, it can't be 0. 86.9, which is 87. That makes sense. Good. See, my eyesight didn't see the 0.9. My eyesight was seeing 0.0, but then I realised that looking at the values, that couldn't be true. Okay, now this time we'll take the bottle off and roll it down without the bottle. Okay, medium-sized wheels, roll down. Ooh, it went to 108 centimetres. So 108. And 108. Very reliable. Any teachers watching this, you need to do these sort of experiments with the kids need to do these. They need to collect their own data and then analyse their own data. It's very helpful. It's a massive, and science in the real world. 108 plus 108 plus 107.5 equals, divided by 3, that will give me 107.8 or something like that. Yeah, 107.8, which I'll just go 108. And then that brings us to our final wheels. Let's put on the big wheels. I feel like I'm like a F1 race meet, you know, just changing the wheels in the pit. Probably doing it at about the same speed, maybe a little bit slower. But I don't have all the equipment. I don't have the rattle gun to put the nuts on the wheels. Okay. Small wheels. No, big wheels. Big wheels. Big wheels, no trouble. Ready, set, go. Rolling, rolling, rolling. Put that back on. What do we got? 122. 122. 122. Size of the wheels. 120. Size of the wheels is making a difference, people. And 120. So the average is going to be close to 121. 122 plus 120 plus 120 equals, divided by 3, 120.66. We'll go 121. And then our final thing, let's pop the bottle of water on. Now, it's interesting because I am detecting that this water sloshes around, which then makes me think there could be another experiment. And another experiment could be, what happens if we use sand instead and the sand doesn't slosh around? I think the sloshing is really causing something unusual to happen. Yeah, this sloshing backwards and forwards is forming a sort of a braking sort of thing, 99. But you know how I just said that the sloshing is forming like braking? You know, this is how innovations occur. You'll observe an interesting phenomena, right? You'll observe an interesting phenomenon, and then you might go, I wonder if we could use that as a form of braking in a car. You know, could having some type of sloshing cause something to slow down when you want it to slow down? You know, that's how discoveries are made. That's how new products and new systems are come up with, by someone observing and someone applying it, their observation, and applying it to the real world. Hey, science, engineering. 100. What I am not concerned. I'm quite fascinated that our results. Our results are so consistent, reliable amongst the trials. This is really surprising me. That one was 203. You know, that's got to be right, eh? I say how reliable it is, and then the next one's 4 centimetres longer, which is actually only 4%, which is not much. Divided by 3 gives me 101. 101 Dalmatians to finish off the thing. Okay, now we do the exciting part, which is actually graphing this. So we can do rolled a distance and wheel size. This was a really good experiment. Sorry. The diameter, we're going to go here, diameter, and we go from 3 to 4. So in actual fact, I'm actually going to start with a 0. I'm going to go 1. No, I'm going to go up by halves. 0.5, 1, 1.5, 2, 2.5, 3, 3.54. And then this on the vertical is our dependent, which is the dependent variable in centimeters. So we've got the independent variable, which is the diameter, because that's what we chose to change, and let me spell that correctly. And then we've got the roll distance on the vertical, which is the dependent. And our maximum roll distance was up to 120. So what that means is we can't go up by 10s because then we won't go far enough. Oh, I hate going up by 15s because it's really hard to work the different values out. I'm going to go up by 20s. 20, 40, 60, 80, 100, 120, 140. Now I really like to try and use most of the graph paper. I've used 3/4 of it, so good enough. Okay, so without any load on it, let's do trial 1. Diameter of wheels 3 centimeters, which is here, and 92. So I go up to 90 and then 2 right there. What about 3.5 centimeters? It goes up to 108. So there's 110 and there's 108. And 4 centimeters, it goes up to 121, which is about here. Nice. 3 values. To be honest, just needed a ruler. To be honest, this is a fairly limited data set. Okay, a fairly limited data set. So, what? No, this can't be true. This can't be true. This is just too, this can't be true. Why am I so flabbergasted here? Because I put my ruler down on those 3 points to drawing in a line of best fit, and the ruler extrapolates it. Where does it extrapolate it to? 0, 0. It can't be that good. That has to be a fluke. When I say it can't be that good, I'm talking about the equipment, of course. I'm not going to go that far. That's just insane. What does that actually mean? It would actually mean if the diameter of the wheel was 0, there'd be 0 roll distance. But that's true. This is incredible. It's too good to be true. So yeah, okay. All right, let's do the next values. Now, normally you'd use a different color pen, okay? But I think they're set down quite a lot, so we don't have to worry about that. Okay, with 100 ml water on it, the 3 centimeter one only went to 72, which is about 72. I like using crosses as well. The 3.5 centimeter one went to 87, which is, there's my 80, there's my 90, there's 87. And the 4 centimeter one went to 101, which is here. Okay, now this time, yeah, it doesn't go to 0, but very interestingly, those 2 lines are parallel. This is all too much for me. Okay, so this is this line here we would say no weight. Okay, no weight. And this line here we say 100 ml or 100 grams of weight. So, are you able to explain the difference in your findings? Now we're talking about, we'll say something like large wheels roll furthest. Yeah? That's just what we found. Why? I think because every turn, for every turn of the wheel, the cart goes further, but for every turn of the axle, there's a certain amount of friction. So when you've got the little wheels, there's more rotations of the axis, and so there's more friction, okay? Due to less friction occurring in axles. Agree? Agree. But with load, surprisingly, distance reduced. That's surprising to me. I would have thought that it would get more momentum coming down the ramp and keep going. Possibly due to the sloshing, but I think sloshing and increased friction I think with the extra weight you also have got extra friction on the axle, and I think that could be an issue. Okay, so what we can say is that the roll distance is directly proportional to wheel size. There we go. If you double the wheel size, you'll double the roll distance. That's what directly proportional means. If you half the wheel size, you'll half the roll distance. Can this be tested? Absolutely, this can be tested. I could actually make larger wheels. We could make larger foam wheels and actually see how this line, whether this line continues on it as a straight line or whether something else. This is worthy of further investigation. It's definitely worthy, but I'd have to make larger wheels. I'd call that a highly, highly successful investigation. Relatively straightforward to do, but with some fascinating results and some fascinating insights. If you find nothing about this interesting, then physics probably is not going to be your game in the future. Okay? But if you found some of this interesting, you might be heading down the world of the science. Might end up looking like me. Woo! Okay, everybody. Bye for now. Glad to have you along. See you later. Bye-bye. Hey, welcome to Lesson 17, Exploring Forces Part 1 of the Year 8 High School Physics course. Now strap yourselves in because this is going to be a real physics lesson. Not that the other ones haven't been, but this is it, my friends. So we're going to be looking at forces today, and forces can be pushes. I'm sort of pulling something. Pushes or pulls. And if you grab your syringe out of the set, if you pull on the syringe, it requires a force. If you push on the syringe, it requires a force. So we're going to be looking at forces later on this lesson. But first, we need to have a look at mass. Now, I've got an apple here that has a mass of about 100 grams. Okay, pretty close to 100 grams. And let's just test that actually, because I'm just sort of like guessing that. So I might just put my scales here and turn the scales on, and I'm going to put the apple on and we'll just exactly see how many grams it is. It's 108.70 grams, which I was pretty close. I took too much off. It's not 100 grams anymore. Anyway, very, very close to 100 grams. This is how much matter it has. Now, have you ever considered what a gram is or what a kilogram is? Did you know 1 litre of water has a mass of 1 kilogram? That's actually quite amazing. I'll tell you what is a kilogram. about, I don't know, 100 and something years ago, a bunch of scientists in Europe got together to determine the standard for mass. And the standard for mass was going to be was the kilogram. And so they made this chunk of platinum iridium alloy. And it's kept in a double glass vacuum sort of container in a vault, and it's called Super K, Super K. And it is deemed to be exactly 1 kilogram of mass. It's the only object in the whole world that has a mass of exactly 1 kilogram. It is the standard. Now, surrounding it, I believe there's 5 others that are very, very, very close, but they're not exactly the same, because don't forget, things are made up of trillions and trillions of atoms. And so if you've got 2 chunks of platinum iridium alloy, even though you try and get them exactly the same, you're still going to be some atoms out, and so the masses are going to be a little bit different. So we've got one there that we say is 1 kilogram. And for a long period of time, it was deemed to be the definition of 1 kilogram, all the way up to 2018, which is only like 6 years ago. The definition has now sort of changed a little bit. I'm not going to talk too much about that now, but that 1 kilogram was it. So why is that important? Well, let's say that you are a manufacturer that makes scales, and there's a company called Wedderburn, okay? Now, Wedderburn makes the scales like this, and it's got a spring in there, and when you put an object on it, gravity pulls down on that object and it compresses the spring, causes this to go down, and you can read that it says 50 grams. Whoa! That's because this scale is not calibrated to 0. It's got a 0 error. So there's nothing on it, and so what I need to do, there's a knob here. Now I need to rotate. I need to rotate this knob so that when there's nothing on it, is it moving? I think it's moving. Look at that. I don't even think I can calibrate this one to 0. Look at that, I can't. So, this is what I need to do. If I want to weigh something properly, I get some mass, I put it on, and I'm just going to remove it, and see how it's now on 0? I think that's pretty close. I've now zeroed these scales. And so now if I put the apple on, I can see that it goes to the 100 grams. See that? Whenever you're using a piece of measuring equipment, you should make sure that it reads 0 when it should be 0, to avoid what we call 0 error. Okay? Now, how does Wedderburn program its scales to read exactly 1 kilogram when 1 kilogram is on it? Do you think they take the scales over to France, go to the, the vault, get the glass jar off, get Super K out, put Super K on, and Super K goes on, and it goes pretty close to 1 kilogram, and then they make some adjustments to their scales until it reads exactly 1 kilogram. They don't make adjustments to Super K. No. They have to adjust the scales to calibrate the scales to that 1 kilogram. But there's no way in the world they'd be allowed to get Super K out and do that. No, because Super K is too valuable. Imagine if, not that you dropped it, but imagine if you brought it out and it added a bit of corrosion or something and it changed its mass, then you wouldn't have a kilogram in the whole entire world. You wouldn't know what a kilogram was. No. The CSIRO in Australia, the Commonwealth Scientific Industrial Research Organisation, which is generally funded by the government, it's the government's scientific body, basically. They've got a briefcase of special balls like this. And these balls weigh or have a mass very, very, very close to a kilogram. And once a year, they are allowed to go to France, and they have to wear special felt gloves and that sort of stuff. And they can compare the weight of their 1 kilogram to, not to Special K, but to his brothers and sisters. And they might have to polish it a little bit just to remove a bit of corrosion that's formed over the year. Get it back to exactly the 1 kilogram, or as close as you possibly can. Bring it back to Australia, and then Weatherburn scales can go to the CSIRO, probably at Linfield, which is in New South Wales. Get this 1 kilogram replica, put it on, and calibrate their scales like that. Do you get the idea? How important a kilogram actually is? I hope so. All right, but a kilogram is not a force. A kilogram is a mass. But masses have gravity acting on them, particularly on the Earth. And that force due to gravity is called weight, okay? And the weight depends on 2 things. Weight depends on the mass of the object and the gravitational force. So on Earth, the gravitational force is 9.8. On the Moon, I think it's 1.6. So it's a lot less on the Moon because the Moon has a lot less mass. And the weight is equal to the mass, so 1 kilogram, so 1 times 9.8, and so 1 kilogram has actually got a force of 9.8 newtons acting down on it, okay? So let's have a look at these notes here. Gravity is the force which Earth pulls down on an object with mass. Now, all objects have mass. This force is called weight, and weight is measured in newtons. Earth has a gravity of 9.8 meters per second. The weight of 100 gram mass on Earth is, the formula is, and I can go here, the weight is equal to the mass times the gravity. But the mass must be in kilograms. So for example, the weight of a 100 gram mass is the weight equals mass times gravity equals, what's the mass? It's not 100, it's 0.1, because it's 0.1 of a kilogram, times 9.8 equals 0.98, which is about equal to 1 Newton. So what is the weight of this apple? And this apple has 100 grams mass. It's equal to 0.1 kilogram times 9.8, which is equal to 0.98, which is about 1 Newton. So this apple here is pushing down on my hand with a force of 1 Newton. Yeah? A question we can ask is, what size force is required to push this syringe down? What size force do you think is required to push this syringe down? Now that's a great question. And what we can do is we can empty the bottle, put the lid on, and I'll tell you what the mass of the bottle is. The mass of the bottle is 28.25 grams. We'll just call it 28 grams. And we'll put the bottle on the syringe and nothing happens because the bottle's not heavy enough to push the syringe down. So what I'm going to do, we need some water and we need to draw up. Oh, with all my using of the syringe, I've lost the 5mm mark. That's very interesting. Yeah, I've lost my 5mm mark. Oh, I've got another syringe here. Ah, that's better. Okay, so I'm going to draw up 5 ml of water, put that in the bottle, So I've got 5. Pop the lid back on. Okay, no, that's not heavy enough yet. So let's get another 5. Now we're up to 10. Let's test that. Is there enough weight there? No, there's not. Okay, well let's actually bring it up to the, let's bring it up. I'm going to add 50 ml of water. Okay. Remember there's some lines there? Still going. Okay, let's see what size force. Is that big enough? Still not big enough. Oh, okay, maybe I need to just start pouring. Oh no, that's going to spill everywhere. All right, just got to keep squeezing up, pushing it in. Put, squeeze up, push down, squeeze up, push down, squeeze up, push down. Let's try this. Oh, 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 it's going down very, very slowly. So if I pour a little bit out, oh, yep, still going down a little bit. Super, super slow. Pour out a little bit. I wonder whether the friction has sort of changed a bit. Oh, so close. That's it. That's it. So what's the mass? I'm going to put this on here and go like that. There's a total of 59 grams. A total of 59 grams. So how much water was that for me? That was 59 minus 28 equals 31 grams. Okay, so I had 31 grams of water, so it was 28 plus 31 equals, so a total mass of 59 grams. So the total weight was, now it's not 59, it's in kilograms, it's 0.059. 0.059. That's what 59 grams is. That's 59 grams is 0.059 kilograms. So 0.059 times 9.8 equals 0.58. 0.58. 0.58 newtons. So it requires 0.58 or 0.6 newtons of force to push that syringe down. That's quite helpful, isn't it? It helps us understand the sizes of forces. Probably it would take the same force to pull it out, 0.6 newtons. Okay? All right. Secondly, what's the size of the pulling force of the tape? That's a good question, isn't it? Like, you can feel it pulling on your hand, yeah? What size force is that? Well, we can do this together. There's another way that we're going to do this. Just going to dry the table, and the plasticine, this this plasticine actually comes from Kmart. Well, this is where we're currently getting our plasticine. It's a good price and it's a good quality. In the years to come it might change, so maybe when you're watching this video we're not getting it from Kmart anymore, but at the moment we are. It's in 2024. And I'm going to show you what the mass of the plasticine is, because it's quite important. And we'll put that on there. And it's 32 grams. Okay, so the plasticine that you get in your set has a mass of 32 grams. What I'm doing is I'm going to roll it out like a little bit of a snake, okay? And we're going to make 32 equal pieces. 32 equal pieces. And the reason is, if this has a mass of 32 grams, and if we turn it into 32 equal pieces, then each piece will have a mass of 1 gram each. Does that make sense? Because you don't have some scales in your set, but I want you to be able to make up masses of 32 grams, of masses of 1 gram. So I've got, that's approximately 16 centimeters long. 16 centimeters long. And so, what am I going to do? I'm going to cut it. I'm going to use a different ruler here. What am I going to do? I'm going to cut it into 16 equal pieces. 16, so I'm going up by 1 centimeter each. Oop, just dropped one through the hole there, that was a bit silly. I might even just put the ruler next to it like that actually, make it a bit easier. Ta-da! Alright, so I now know I've got 16 equal pieces. That means each piece has a mass of 2 grams. Okay, each piece has a mass of 2 grams. So that is good. Each of those weighs 2 grams, pretty close to. And so what I'm going to do now is I take my scale, not my scale, my tape measure, and I put one of the weights on it and press the button. Whoa! Up it goes. Let's go 2 weights. So we've got 2 times 2, which is 4 grams. And whoop! Oh, don't drop it. 4 grams, 6 grams. Let's see how we go. 6 grams. Whoop. 8 grams. Whoop. 10 grams. Ooh, still going up. 10 grams. 12 grams. Whoop. 14 grams. Whoa, a bit slower. 16 grams. Whoop. 16 grams, and that's it. 16 grams. Now, was that 16 grams? Let's have a look. Let's see how accurate it was, this idea of mine. 16 grams. 19. Okay, so there is an inaccuracy there of my method, but it's not absolute disastrous. So let's see here. It says, determine the maximum weight the retractable tape will just lift. The mass is 16, so you could go 16 divided by 1,000 to turn it into kilograms. So we'll go 16 grams. It was actually, I actually worked, 16 divided by 1,000 equals, oh no, it's divided by 100. 16 divided by 1,000 equals 0.016 kilograms. Times that by 9.8 gives me 0.16 newtons. 0.16 newtons. So this tape measure exerts a pulling force of 0.16 newtons. Now that's very, very helpful. It's not a big force, but it's a big enough force to accelerate that empty car quite fast, isn't it? But this is now over to you. You can perform an investigation to see whether that 0.16 newtons is the same for all extensions of the tape. You know what I mean? It could be exerting a force of 0.16 newtons here, but if I extend it like that, is it, whoa, that lifted it up then. If I do it to here, it only just lifts it up. If I do it up to here, oh, that shows me the force the tape exerts actually depends on how much it actually has been, the tape has been pulled out. And that makes sense because you're actually winding up a spring when you pull it out. And the further you wind up the spring, the more force it exerts. Now, if you want to be like, if you want to really excel at physics, okay, and you want to go next level, this is what you can do. You can work out what the pulling force is for 10 centimeters. You can work out the pulling force for 20 centimeters, the pulling force for 30 centimeters, the pulling force for 40 centimeters, and you can then graph it. And you will graph the pulling force on the vertical versus the extension of the tape and see what the line of best fit looks like. Okay, well, thanks so much for joining me today. Hopefully you've got a little bit more of an insight into mass and weight and forces. Okay, I'll see you again soon. Bye for now. Lesson 18, Exploring Forces, Part 2 of the Year 8 High School Physics course. Now in this lesson, we're going to be actually investigating and trying to determine the strength of some of the magnets. Now, when I talk about strength, if we pull out the 5 large magnets, and we'll put the small little magnets back, and we make sure we keep these away from little kids, okay? We definitely do not want little kids getting their hands on these. But if you pull the magnets with a certain force, you can pull them apart. Now, what about if I just get 2 magnets? And that actually seemed a little bit easier. Now, when I say easier, I mean less force was required. But what is the size of this force? Do we have the tools to measure it? Well, here's one thing I want to say. I was a physics high school teacher for many, many years in a school, and the school had quite a lot of money, and I was able to buy quite a lot of equipment. And generally what I find is that when teachers buy lots of equipment, a lot of it doesn't actually always get used. It just like sits in the cupboard and that sort of stuff. Since leaving teaching and starting my tiny science lab business, I haven't had access to, number one, all that money, 2, all the equipment. And so I've had to innovate, come up with ideas to use the equipment that I actually did have. Now, the equipment that you've got is the high school physics set. And so we're going to try and work with that equipment to work out what the force is between these 2 magnets, okay? And we've got to be innovative. Now, what do we know? Well, we know that this bottle weighs 28 grams. That's the first thing that we know. We also know that this bottle has got markings on it, 50, 100, 150, 200, 250 ml. So we can actually measure the amount of liquid in this bottle. We also know that 1 ml of water equals 1 gram. So we've actually got a way to make weights. So if I get this bottle and I put in 50 ml of water, okay, 50 ml of water, I should actually put it down here, and so I avoid what's called parallax error. There we go. That's 50 plus the 28. That should be about 78 grams. Now, one thing I noticed in a previous video when I was editing it was I can actually read the scale quite well from this angle, but looking straight down on it, you can't actually read the scale. It's due to some polarization of that lens. So that is actually 69 grams. 69 grams, so pretty close to 70. What did I say it was? I said it was 78. So I'm 8 grams out, which is about a 12% error, which is relatively high. Okay, it's relatively high. So what that means is I should have really gone just really up to the line and even the tiniest bit past it. Okay, there we go. That will be 50 plus 28 equals 78 grams. So what we're going to do is I found that we want to measure the strength between these two magnets. And so we can hold one magnet with our hand, but how do we attach this other magnet to the bottle? We don't want to use glue. I can tell you that now. Okay, that would be quite painful. But what I am going to do, I'm going to put the lid on the bottle, wherever the lid is. Can you see where the lid is? I just can't see the lid anymore. The lid's gone. Maybe, put the lid on this Coke bottle. Hang on. I think that could, maybe that was the, no, 78 grams. All right, what I've discovered, you see the rubber tube, the silicone tube that goes on your syringe? I've discovered that you can actually push the magnet into it quite well. And when you grab it with this other magnet, it's really stuck in this tube. So that's good, because if I put our elastic band around the bottle a few times, twice we'll probably do, and if we wrap the tube through the bottle like that, we can actually lift the bottle with the tube and the magnet. So what I can do is say, if I can lift now, look at that. The magnetic strength is stronger than that 78 grams, or the weight of the 78 grams. Isn't that good? So now, let's do 100 ml and see what happens. So I'm going to add 100 ml. There we go. Put the lid on. And it's stronger than 100 plus 28, 128 grams. Okay. Let's go to 150. There we go. I keep putting that lid on the bottle. I need the lid on this bottle. Whoop. And, there we go. Will it lift it up? Wow! Okay. We need more water. 50, 100, 150, up to the 200. Wow! we will have a problem. We will have a problem if it's stronger. I'm going to fill it up all the way. Oh, this could be a problem. Okay, now that's got 250 ml of water. I'm really actually hoping that that it won't lift it up. That's what I'm hoping, because otherwise, this will be difficult. Don't lift, don't lift. Yay! It's like, why are you cheering that you can't lift it up? Because the bottle's full and I'd have a big problem. Okay, so now what do I do? Well, I can actually start withdrawing water. So I'm going to take out 10 ml. So now I know I've got 240 ml in here. 240 ml. Will it lift it up? Oh, not quite. What about, sorry, not 240, 245. 245, because I'm only taking out 5 ml. Now it's got 240. Now it's got 240. My mistake. Now it's got 240. Oh, this is, you might need a pair of pliers actually. That's it. That's it. I'm going to call it. I'm going to call it and say that that magnet can lift up, what do we got? 28 grams plus 240 grams equals 268 grams. What is that in kilograms? 0.268. And so the total weight is equal to the mass in kilograms, 0.268 times 9.8. So let's put that into the calculator. 0.268 times 9.8 equals 2.6 newtons. The magnet, well, I shouldn't say the magnets, I'm going to put the magnet exerts a pull of 2.6 newtons on each other. Okay, the magnets is okay, that's fine. I'll fix that up, magnets. Wow, isn't that interesting? Now you could actually investigate a little bit further, you know. You could actually, if you were so super keen and wanted to really dive down deep, is what I've been doing is working out the strength from one magnet onto another magnet. Does it make any difference? Does it make any difference if we use two magnets together pulling? Does that change the force? What about three magnets pulling? Does that change the force? That's an investigation, and it would have some interesting results, whether you can increase the magnetic field by adding more magnets together. I suspect, this is my suspicion, that if I have one magnet, it will be able to exert a certain force. If I add two, the force will increase, but not double. I don't think it will double. The force will increase. And I think if I add a third, the force will increase just a little bit more. But maybe by the time you've added the fourth, it won't make any difference. There'll be a point where it makes no difference because the magnetic field strength is just too far away. That's what I think will be the case. But you'd have to investigate that hypothesis. There you go. Now, this was the strength of magnet to magnet. Oh yeah, and somehow we have to get this out of the tube, which you can do by squeezing. You can actually squeeze the magnet out of the tube. Here's my question. What's the strength of these magnets to steel? Look at that. I can pick up the steel ball, and the steel ball weighs 33 grams. Now, there we go. I really probably should actually just lift it up with one of the magnets, to be honest. There we go. I should pick it up with one magnet. Okay, there we go. So it's at least 33 grams. We could use the bottle method somehow, but we'd have to, I'm not too sure how to actually strap the bottle in there. So there is another way, and the other way is to get our plasticine out again. Okay, get our plasticine out again and roll it out to 16 centimetres, as evenly as you possibly can. Okay, so rolling it out to 16 centimetres. That is pretty good. And so that has a mass of 32 grams. And what about if this time I just actually chop it up into 2 centimetre lengths? Okay, so I'm just going to put a mark at every 2 centimetres, 8, 10, 12, 14, and I'm going to use those marks as my cutting marks. It's very satisfying cutting plasticine with the ruler, I can tell you that right this second. So what's the mass of each one of these? Approximately 2 grams. Okay, approximately 2 grams. And so I need my steel ball, and I'll put my steel ball tucked into the, now I don't want it to stick to the table, so I've got the steel ball plus 2 grams. Will it lift it? Nope, that won't lift it. Let's add those magnets all together. Oh, that won't lift it either. So the magnet is strong enough to lift the ball, 33 grams, but it's not strong enough. Oh, yep, yes. There we go. It's better to hold it in your hand because it's not going to stick. So that's holding up 2 grams of plasticine. Let's get another 2 grams of plasticine. So 4 grams of plasticine. Oh, no, it won't lift up 4 grams. So what I'm going to do is I'm going to cut one of those pieces in half. Stick it on. Oh, it's picking up 3 grams of plasticine. Okay, so that's as far as I want to go. So 33 grams plus 3 grams of plasticine gives us 36 grams, which is 0.036. To get from grams to kilograms, you need to divide by 1,000. So the total weight is equal to 0.036. And so the magnet has a pull on a steel ball of 0.036 times 9.8 equals, whoa, that was totally wrong. 0.036 times 9.8 equals 0.35 newtons. 0.35 newtons on, not each other, on the steel ball. I'll fix that in when I do an edit on the sheet. All right, now what about the bar magnets? Okay, so we've got 2 bar magnets, and those bar magnets are not very strong. It says determine the strength of the red-blue bar magnet, magnet to magnet. How are we going to do that? Well, we could do the old grab the 2 gram piece of plasticine and stick that into the plasticine, couldn't we? And see if that lifts up. Way! 2 grams of plasticine. The big question is though, what's the mass of the magnet? All right? Well, actually, let's just find out how much plasticine it will lift up. Will it lift up 4 grams of plasticine? Yay! 4 grams of plasticine. What about 6 grams of plasticine? Yay! 6 grams. What about 8 grams of plasticine? Oh! 8 grams. Only just. So I might add 1 gram. So we got 9 grams. Will it do 9 grams? Yes. swap the 1 for a 2, so now I've got 10 grams of plasticine. Whoa, this is stronger than I thought. 12 grams? What? $14 grams? I really don't want it to actually... Nah! Oh! Oh! Well, I'm going to say 13 grams of plasticine. So it can hold 13 grams of plasticine, but it's also holding the weight of the magnet. Now, I could tell you the mass of the magnet. I could tell you the mass of the magnet, but I'm not going to. Instead, I'm going to tell you how you can work it out. If you put your ruler there and you put a pen in the middle of the ruler so that it sort of balances, I might actually just put a little bit of plasticine so that the ruler can't move. Then I want to try and balance this as close as I possibly... There we go, that's balancing. Put your magnet on that side. Now if I put it... Look, let's balance it, sorry. If I put that magnet on that side, if I put an equal mass, like another magnet on the other side, right, then the two will balance. See, they'll balance out. So what I can say is the mass of this equals the mass of that, but I don't know the mass of this. But I do know the mass of some lumps of plasticine. So if I put 2 there, nothing happens. Now I've got to make sure it is in the center. There we go. What about 4 grams? Here we go. Thankfully I didn't stick my plasticine too much together. 4. Whoa! Look at that. It's pretty close. It's pretty close to 4 grams. Okay? Now, I am not going to write out this for you. I am going to say that the magnet has a mass of 4 grams, and you can work out the mass of plasticine used, and you can draw a drawing of the setup yourself. It's very easy to wait for me to write it down and draw the picture and then copy me, but it's over to you now. Now it's time for you to actually do this. It's not too hard to draw a picture of a piece of plasticine with a magnet embedded in it and lifting up with another magnet with the force like that. So if you do that, then you get down to point 4. It says determine the strength of the red blue bar magnet to steel, magnet to steel, and it says hint, use the pan. Oh, because this magnet is not strong enough to pick up the steel ball. But in your sets is a little square steel pan, and that will help you. Okay? So I'm going to leave that one to you and see how you go. Thanks for joining me today. I look forward to seeing you again soon. Bye. Hey everybody, lesson 19, Exploring Forces, part 3. Now, we're going to do a few little interesting activities today, and you're going to need from your set, you're going to need your ruler, okay? You need your plastic ruler. You're going to need a paper clip from your set. There'll be some paper clips there. You're going to need your plasticine from your set, and your little vial of super magnets from your set. And finally, you will need to find some thin string. Okay, this is cotton thread. Cotton thread's very good. Really thin braided fishing line would be okay. Normal fishing line, the problem with that, it's quite hard to tie it, so I don't think normal fishing line would be very good. But dental floss. Hey, yes, you could actually do this with dental floss, 100%. You could fix your teeth up too while you're at it. Joking, I can't see your dirty teeth. Okay? I just had lunch. I've probably got dirty teeth. Can you see what I had for lunch? Thai. Oh, yummy. All right. So, magnets can exert forces on each other, on other magnets or magnetic metals. And, well, what are the magnetic metals, do you think? Do you think all metals are magnetic? Yeah? Well, you'd be wrong. Iron, nickel, cobalt are the main magnetic materials. And then there are a number of rare earth ones, like neodymium is a magnetic material. There's a few what we call rare earth minerals or metals that are magnetic, and they can produce some very strong magnets, very powerful magnets, which is why the world is trying to dig up more rare earth metals because of the strong magnets they can make. And if you've got a strong magnet, you can make strong electric motors, strong speakers, loudspeakers, strong microphones. So yes, very strong magnetic materials are very, very important. Okay, now don't forget that forces can be a push or a pull. And we're going to investigate some pulls in this lesson. And you might need like a chair or a structure, something like that. What I've done is I've got an old retort stand that will act as my chair. And I've got just a piece of threaded rod here. Oh, it's chopping through my face. And I'm going to get out the 5 large supermagnets, and just attach them to the end of that retort stand. So there they are right there. You might need to sort of attach them to a chair somehow. Now, if you look under the chair, maybe there's a screw that goes up. Well, that screw might be magnetic. Anyway, somehow you need to get these magnets fixed in place. Then you get your very light string, and I don't like how this bar is chopping through my head. I might just temporarily move it up a bit. There we go. That's better, isn't it? Now I don't have a bar through my head. Get your fine string, thread, and you're going to tie it to your paper clip. Okay? Tie 1 knot. Just very basic knots, really. Another knot. Just going around and through. I might even just do it a 3rd time, just around and through. These are called granny knots. And the more you do, the stronger it is. Okay, so now I've got the fishing line like that. And I'm then going to, I might actually, I think this might work well, where I put the vial over the fishing line like that, and then I'm going to just push the plasticine, and I'm going to tighten this up like this. And what I'm going to do, I'll move here. I'm going to bring it a bit closer. I'm going to go up. I'm going to get close. Put the vial like that. Okay. I'm trying to suspend Can I get it? Ah! I've done it. Oh, I haven't done it. Oh, try again. Oh, not easy. Now you know I need really light fishing line. I mean really light string. Oh. Oh. Ah. I don't want it to stick up there. I just want it to levitate. Ta-da! Look at this if we go around. Woo! I can blow it. See how it goes around in a circle? Might do it so they can... I love it. Look at this, give a little bit of a push. So there's a 1/2 centimetre gap up there. It's like the paper clip is like hovering, levitated, magic. Might even get the ruler. Okay, the ruler. Now this is not a magic trick. I'm going through. Way. Ready? Through the gap. Zoo. 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 I even might move that. Well, dopey. Come back up. Okay. Yep. Look at that. You see how it's twisting backwards and forwards? And go through with the... Well, bang. Okay. So, what we're going to do is we're going to draw the forces acting on the paperclip. We're going to do what's called a free body diagram. Now, don't let that freak you out. So, what are the forces acting on the paperclip? Well, it's being pulled down, okay? It's being pulled down by gravity. So I'm going to do an arrow down. So that's the first thing. It's got some weight pulling it down. But did you notice how the string's quite taut as well? The string's quite taut. It was actually pulling down as well. So I'm going to put a second force. I'm going to put a second force, which I'm going to guess is a bit smaller than the weight. So I've done it a bit smaller than the weight, and I'll put the string tension pulling down on it. Now, if these were the only two forces acting on it, do you know what it would do? It would accelerate down, but it wasn't accelerating down. It was staying at the same place, and it wasn't changing speed. It had zero acceleration. That's because there was a magnetic force pulling up on it. Okay, there was a magnetic force pulling up on it. So what a free body diagram does is it shows the forces clearly acting on the object. Now, I can actually add those forces together, but I don't add them like you'd add normal numbers. I don't add like 2 plus 4 plus 6 equals 12. No. I have to add them and make allowances for their direction. So, these are called what we call vectors. Forces are something that we call a vector, and that is that the size is very important, but the direction is also very important. So the magnetic force is up, and the weight force is down, and the string tension is down. So you've got a size and a direction, in this case up and down. So I'm going to put, what was the first force I put in there? The first force I put in there was the weight force, which was down like that. So I can call that the weight force. The next force that we're going to add to it is the string tension. And the string tension was only about, it was less than the weight force. It was about that big, so that was the tension. But the force up due to the magnet was quite large, and we're going to start it here, and we're going to go up, 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 all the way to the very top there. And what we actually have is what we call a resultant, okay, equal to 0. That means when you add those forces up together, you get a 0 resultant. a zero, or what we call these balance forces. These balance forces don't change the circumstances of the paperclip. That's why it hovered there. Okay, let's do another slightly different and slightly, I think, more interesting setup. So in this case, I put this here and I get my paperclip like this, and I'm going to come at an angle this time. Okay, I'm going to come at an angle this time. Let's see. I'll put my lump there. Oh, okay. Oh, I'm trying to make this thing hover. Might try adding a ruler so it doesn't bite into the plasticine as much. Oh, so close. Ah! Okay, I think I'm going to make a change. I'm going to put them sideways this time. And I probably will put a piece of sticky tape around them so that they can't move. I think that might be important to this scenario as well. We have to have these magnets fixed in position. We can't have them moving. All right, that sticky tape, that's really going to do a good job. I'm being serious there, it actually is. Now get my string and pull some out. Da 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 da. We can do it. Come on. Oh. Okay. Sometimes you've got to make adjustments in life, don't you? But these magnets, okay, what about if I put them side by side? What about if I try and put some magnets side by side? That might, uh-oh. This tape's not going to come off, people. It's stuck to itself now. Ah! Come on, please come off, tape. Otherwise I've got to get some scissors. Let me just grab some scissors, please. Okay. I'm going to slip, go sideways here. Not everything works straight away. So you know what? Just give up. If it doesn't work straight away, give up. Don't show any perseverance. Wouldn't want you to do that. Okay, so I'm actually going to fold them in half, and I've got them sideways together. So I've actually got more magnetic field pointing in the direction that I want. Okay, will that make a difference? Okay, let's try that, shall we? And might just move this backwards, sideways a bit. Come on. Please hover, levitate. Not quite. Like I can make it stick there like that. Woo! It actually feels quite good, you know. There's a bit of tension in that string, but it's not what I want. Okay, it's not what I want. Ah. What about if I try less angle? Okay, let's try less angle. Let's try a steeper angle. Let's see whether that makes it a bit easier to get our outcome that we want. Let's try that. How are you going? Are you having any success? Because I'm not. Okay. All right. Let's try something different. Let's try something different. What are we going to try? What about... Take that off the iron. Take that sticky tape off. Like that. And this time, instead of the paper clip, what about if I try tying it, the string to the magnets? Right? Why don't we try that? And I think 3 magnets is too many. Even 2 magnets might be too many. I'll just pop them there. Well, what about if I put the magnets up here? So 3 magnets up here. Right, 3 magnets up there. Because from previous experiments, we've found that the force of magnet to magnet is stronger than the force of just magnet to steel. You know, that's actually something we've found. And I'm going to put a bit of sticky tape on the magnets. Okay. Let's try that, shall we? So there's my magnet. Will it be a... Oh, yep, it's definitely attracted up there. Okay, and now I'm going to stick these magnets up here with a bit of sticky tape. Like so. All right, now let's have a go. Let's pull this back a bit. Come on. Oh, there's a good attraction there. Come on, please. Oh, so close. Oh. I think it's tearing through the... plasticine. That's sort of the problem. So I'll put the plastic ruler there. I'm going to just move this out of the way a bit. Oh! Oh! Look, people! I can give it a little bit of a wiggle as well. Look at that! Now that's exciting. I can't get my ruler. I wonder if I can put my pen through it really quick. Whoa! Look at this! Ready, set, woo! I can put my pen through the gap plastic pen. It is levitating. 2 magnets here, 2 magnets there, tied with a piece of string. I can sort of like, I wonder if I could make like a what's it called? A flying fox. Here we go. I've got a paper clip here. I'm going to see if I can do a flying fox down the oh! Can I do a flying fox? Let's see. Oh, it dropped off. No, the weight was a little bit too much. Obviously it would work if I like just click the magnets together. See that? Then I can do the flying fox. Whee! I could even put a little person on the flying fox, I think. Take a bit of plasticine. Make it nice and taut. Here we go, let's put a little person on it. It's a piece of plasticine, good enough. Yay! Look at that. So, how about, whoa, there goes my string. How about we do the free body diagram for that scenario? Let's move that out of the way. Okay, so let's draw this free body diagram. And so we will have a weight force acting straight down, a weight force acting straight down like that. And we can label it as the weight force. Then we're going to have some force due to the string, okay? And that will be heading that way. Now, it'll probably be less than the weight force, so we'll call that the tension in the string. And then we're going to find that we've got a fairly strong magnetic force, okay? A fairly strong magnetic force like that. So forces that are strong are going to be longer. They're going to be drawn as longer vectors. Forces that are shorter are going to be drawn as shorter vectors. And we're now going to add those three forces together. And so we start with the weight force. Okay, we start with the weight force, which I drew as 3 centimeters. Now, it doesn't mean I would have got them all exactly right. So there might need to be a little bit of some changes. Then the magnetic force. Okay, the magnetic force was, remember I said it was quite strong. So I'm going to head up here quite strong. There's the magnetic force. Magnetic force. This is the weight force. Now, when it was hovering there, when it was just like levitating, was it speeding up? No. Was it slowing down? No. Therefore, its acceleration, its change of speed was 0. Therefore, if you add up all the forces, they'll add up to 0. And so the final force which we add goes from here to here. There we go. We've now got this closed triangle, and this was the tension. Look at that. This shows us that those three forces, when you add them together, end up as balanced. 0 net force. Now, it's okay if you're not getting your head around this. You know, this is the sort of stuff you're doing Year 11 and 12 physics and engineering, okay? Free body diagrams. But there's nothing wrong with getting a bit of a taste for these things, because later on, if you do officially learn them, they'll be easier to learn, okay? So there we go. Hopefully you've enjoyed this lesson, had fun levitating your magnets, and I look forward to seeing you again soon. Bye for now, everybody. Hey all, welcome to lesson 20, mapping magnetic fields in the Year 8 high school physics course. So in this lesson, we're going to be mapping the magnetic field around, well, one magnet and then some arrangements of different magnets. And so for this experiment, or actually not an experiment, it's actually an investigation. For this investigation, you're going to need the 2 bar magnets. Remember, these ones are actually fairly weak, not in terms of, well, they're weak in terms of their strength. If you actually drop them onto some tiles or concrete, they'll break. But they also don't have a very strong magnetic field. But for this activity, it's strong enough, I can tell you that. You'll also need your iron powder, which comes in your physics set, and you'll need your plasticine. And what could be helpful is 2 thin books, for example, 2 like Mr. Men books. You might not have ever heard of them, but they were around when I was growing up. Mr. Grumpy, Mr. Happy, Mr. I don't know, Mr. Bump. But you could also use some cardboard, or you could also use some paper, but I'll show you what that's for. All right. So I've got my sheet here, and the magnet is going to start off with the North Pole there on the right. So I'll pop there like that. I'll pop that there. I want to get this roughly in the right position. And then actually put this wood around it so that when I put the paper on, there's something there to support. There's something there to support the top piece of paper. Okay, so that's what that wood is for. It's so that the paper is supported. Then, with your iron filings, pour them onto the lid, maybe about half or something like that. And a word of warning, try not to get iron filings on your magnets because they're very hard to get off. Then I'm going to Salt Bay the iron filings onto the magnet. Okay, so, and I'm not just onto the magnet, but surrounding the magnet. So a magnetic field is an area of magnetic influence around magnets. Not just magnets, but electromagnets, which are coils of wire carrying electricity. So around I go. Take it slowly, take it carefully. Try not to like overload one particular area. We're going to do something quite interesting at the moment that will bring it to life. And what will bring it to life is a bit of a tap, right? If you give it a little bit of a tap, you can actually start seeing the patterns forming, and you can also then sort of see some zones where you might want to put a little bit more in. And if I go tap, 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 what we can see is that we've got these magnetic field lines going from pole to pole like this, and then they sort of bulge outwards. Here we go, we can see them going from pole to pole, and then we can also see them extending out into infinity. Okay, they're extending out into infinity like that. That is that looks really, really good. I really love how clearly you can see these magnetic field lines leaving and coming into the magnet. Now, what I'm going to do is just give that corner of the paper a bit of a squeeze, and so I can then funnel the iron powder back onto that lid. And then what did we see? Well, starting at the north, we've got a magnetic field line coming out like so, and going into the South Pole. Now, by definition, scientists have described that the magnetic field lines go from north to south. Okay? They could have decided that they went from south to north, but nope, they've decided magnetic field lines go from north to south. Okay, so here we go. Magnetic field lines never cross. They leave the surface at right angles, so perpendicular. These ones head off into infinity, and the further you are away from the magnet, the stronger the magnet. The further you are away from the magnet, the weaker the magnetic field, and that's indicated by the distance between the magnetic field lines. Where they're far apart, the magnetic field is weakest. Where they're close together, the magnetic field is the strongest. What about now if we do two magnets? Okay, so we're going to do two magnets, and a south there and a north there. And what I'm going to do is I'm going to try and carefully remove that lid. I'm going to get a bit of plasticine and put some plasticine between them. And the reason I'm doing that is, number one, that will stop the magnets from attracting each other and pulling. Well, they'll still be attracting each other, but they won't move towards each other. And also, that little bit of flatness there will also help support the paper. So I'm trying to match that gap to that gap there. I think I've got it pretty good, and I'm trying to make sure that the magnets are, there we go, that feels good. And so now I'll just put the wood there, the timber there, and that looks like a very good setup. The wood's a bit grotty, but that's okay. And if I go like that, I think that's pretty good. All right, let's iron powder this baby. Let's go. Salt Bay. Sprinkle, sprinkle, sprinkle. Don't rush it. Oh, I can see straight away some lines, some parallel lines between the two magnets. That's exciting. All right. Every magnet has a north and a south pole. Every electromagnetic field has a north and a south pole. That's called a dipole. Di means two. I don't think scientists have discovered what we call a monopole. They've discovered a monobrow, but not a monopole. Let's go tap, 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 tap. Wow! Look at this. I love it. Bringing the invisible visible. You know, just because you can't see something with your eyes doesn't mean it's not actually there, believe it or not, people. We can't see magnetic fields with our eyes. Maybe like butterflies can, and bees. Pigeons. No, I don't think pigeons can see them with their eyes, but pigeons can definitely detect the magnetic field of the Earth. Amazing. I'm just going to go a bit in the middle there. Okay. So we've got these lines between the magnets. We've got the lines going from pole to pole, but we also do have a few little lines going from this from the north to the south there. Okay, so I am going to sketch these lines. Let's get rid of that. Pop this here. Ooh, it's starting to get a bit grubby. So definitely we had some lines going from north to south, but I also definitely saw some lines like this, without a doubt. 100% I saw some lines like that. Agree? Then I had some lines that look a bit like this. They sort of wrapped around a bit. Sketching these in. Now this is sort of what I saw, but if you really want to map magnetic field lines, there is a few rules. Okay, one of the rules is the magnetic field lines have got a direction that goes from north to south. Also, the magnetic field lines leave the poles at right angles, perpendicular. They also never touch. Okay, so yeah, there are some rules, and so rather than drawing the magnetic field lines, I'm actually drawing what the iron powder sort of looked like, which gives us an indication of the magnetic field. Okay, so, and then our final one is south to south. No, not south to south, north to north. But I can almost guarantee you that south to south and north to north will look identical in terms of the magnetic field lines. Okay? Let's go like that. Make sure they're a bit closer like that. It's good. Pop this in. Okay, I'm liking that. And what will this look like? Oh, straight away I notice a difference in the middle of the two. Can you notice the difference in the middle of the two? Straight away I can see it. There's no field lines in the middle. See that? That is interesting. Tap, 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 tap. Might just spread that out a little bit and then tap it again. Over here a bit. Tap, 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 tap. Okay, look at this. Nothing here. It's sort of, the lines sort of head out into infinity. See that? They sort of like go zoom, zoom, but then this side looks fairly similar to what we're used to. Wonderful. Let's get rid of this. Pop that there. So we sort of have, go zoom, shoots out, zoom, shoots out here, zoom, shoots out here, shoots out here. Then it looks relatively similar on these sides. Come around here like this. Come around here like this. And then how's that? So, using iron filings, we can visualize the magnetic field lines around our bar magnets. Now, if you want to get really excited, you could do a little project with the other magnets, the super magnets, and actually like line them up and do the sprinkle around them. That would be an interesting thing to do, but that's like an extension activity. Anyway, well, thanks for joining me today. Hopefully you've enjoyed this lesson, and it's been interesting, those field lines in the powder, hasn't it? So, well done, and I look forward to seeing you again soon. Bye for now, everybody. Hey everybody, welcome to lesson 21 of the Year 8 High School Physics course. In today's lesson, we're going to be exploring making magnets, and I'm going to discuss how to destroy them as well. So, for this lesson, you're going to need the paper clips out of the set, the 2 bar magnets from the set, the super magnets from the set. I'm also going to be personally making, and you need some iron powder. You need the iron powder as well. I'm going to be making or attempting to make an electromagnet using a battery, some wire and a nail, but you don't need that. You can just watch me do it. Or you can find a battery and a nail and a wire from around the house and do it yourself. That's good too, but it's not in the actual set. And I've also got a bowl of water here and some paper towel, which I'll explain what I use that for later on. But firstly, let's just see whether the paper clips are magnetic. And the way that I do that is by seeing if I can pick up any other of the paper clips. And the answer is no, they're not moving at all. And so they might be slightly magnetic, but they're certainly not powerful enough to pick up another paper clip. What about a little bit of iron powder? Because iron powder is very, very light. Will the paper clip pick up any? Now look at that, it's picked up the tiniest amount. It's picked up the tiniest amount, which probably indicates that it's very, very weakly magnetic. Okay, but just keep that in mind, that it only picks up a little bit. Now the main magnetic metals are iron, nickel and cobalt. Iron, nickel and cobalt. And paper clips, most things that we have around the house are made from iron or steel. Iron, if you add a little bit of carbon to it, it causes it to become harder and more useful. And that carbon hardened steel, iron, is called steel. Okay, so that's what steel is. Steel and iron are basically the same thing. So there's lots of things around the house made from steel or iron. And so for these scissors, if I get the magnet, you can see that it's made from iron. Okay. Now, is this pair of scissors magnetic? Well, I could bring the, whoa, look at that. Huh. these scissors are actually already magnetic. Not too sure why that is, but they do have some magnetic strength. How do we make a magnet? Well, all substances, objects, are made up of particles. And this paperclip is made up of paperclip particles, or it's not. It's made up of iron particles, okay? Individual little iron particles called atoms. And in iron, these groups of sort of atoms form what we call magnetic domains. Okay, and a magnetic domain has got like a little tiny north pole and a little tiny south pole. But because it's not magnetized, what that actually means is that all these magnetic domains are sort of in random positions and random directions. And so they're not working together at all. Think about a tug-of-war team. You've got like a couple of people on either side of the rope all pulling together. Well, if you can align these magnetic domains so that they're all aligned and working together, then they should become magnetic. Now, how do we make that happen? Well, we can make that happen by getting a bar magnet, okay, getting a bar magnet, and stroking the paperclip. So I take the red part of the magnet and I go stroke, 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 like this. I'm actually running it along the paperclip metal, okay, and I'm coming up and then coming around and going down and across, up, across, down, rub, up, across, down, okay, so stroke. And what I'm hoping to do is that over time I cause those magnetic domains to line up, and I'm hoping that it might become strong enough to pick up another paperclip. If it doesn't, I'm not going to despair. I'm not going to think I've done something wrong. I'm going to think, well, maybe the magnet that I'm using is too weak. And the answer to that is, well, we have got some stronger magnets in our set. But we'll start with the weak one. All right, shall we test it? Will it pick up the paperclip? Whoa! Did you see that? Oh, yes, indeedly do. Look at that, my people. I have magnetized. I'm going to do a bit more. Boy, that actually worked. Did you see the look of surprise on my face? I think I've done it, people. Here we go. And come on. No. Yeah. It's almost like I've weakened it. I might try it on the iron filings. Let's see what happens on the iron filings, shall we? Ooh. Not heaps. Bit more. Okay, well this time I'm going to get out my super magnets. Dun, 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 dun. And I'm going to use the 5 big ones, and I want to find the north end, and so the north end is going to be the end that repels. That's it. So that's the north end, and this is my paperclip that I've been magnifying, and I'm just wiping off any iron powder, and now whoa, I can actually feel a much stronger attraction straight away. There we go. So I'm feeling a much stronger attraction straight away. So I'm rubbing it with the north pole, so I'm going up and around, up and around, up and around, up and around, like that. And you know what I'm going to do? I'm actually going to rotate that to a south pole, rotate the paperclip around, and actually go the other way now, on the other side of the paperclip, like that. Then I'm going to rotate the paperclip, rotate the magnets, and do one last stroking like this. Let's see whether this has made a difference. Come on. Oh, so close. Look at that! I have magnified the paperclip. There, everybody. We've made a magnet by aligning the domains. Yeah, that is very, very good. Now, I'm going to pop that down there like that. And what I'm going to do is, what's another way to make a magnetic field? Well, with an electromagnet. So I've got this wire here, and this wire's got, it's called enameled copper wire, and it's got a little bit of a plastic coating called enamel on the outside. That's why it's called enamel. And so I actually have to use a piece of sandpaper to remove the coating, because the coating is an insulator, and I need to get some direct contact to the battery pack. Now, that's not coming off so well. So I've got a pair of matches, some matches. Oh. And I'm going to burn off the coating. Now I'll give it one more scrub with the sandpaper, and hopefully that will remove the plastic. Okay, then I'm going to get a nail, an iron nail, and I'm going to wrap the wire around the iron nail. Now the reason we do this is because it makes the electromagnet much, much, much stronger. Okay, by wrapping the coil of wire around the magnet, you'll actually get a much, much stronger electromagnet. There we go. I've got the two ends. Then I take I've got a little battery holder. I'm going to twist one end of the wire of the battery holder to one end of the wire, and then I'm going to do the same for the other one. Twist, 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 like that. And now I'm ready to put my battery in. But before I do that, I'll just make sure that the nail is not magnetic, and it's not. Get my battery pack, put it into the battery pack, and ta-da! And look at this. Well, now it gets hot quite quickly because it's a short circuit. Okay, so it's a short circuit. But so don't have it on for too long, because you'll run your battery out very, very quickly, and the wires will sort of start getting a bit hot. That's actually warmed up. But that is how you can make a magnetic field or an electromagnet, and you can turn it on and off. But that electromagnet aligns the domains in the iron, causing it to be quite a strong magnetic field. But I've got a question for you. Here's my question. So remember, I took this, there we go, so I've got the North Pole, and that's repelling, so that's a North Pole. Then I took this paper clip and I magnetized the paper clip by stroking it. So I've got a North Pole here, and I'm stroking it with the North Pole. Now the big question is, what pole does the end of this paper clip become? Does it become a North Pole, or does it become a South Pole? How can we tell? That's the question. How can we tell? Well, I'm going to show you how we can tell. I think I've magnetized it enough. I'm going to put the bowl of water here, like that you'll be able to look straight down on. I'm just going to get my scissors. Now, I haven't actually done this before. Shaking your head saying, does he actually ever do anything before? Well, usually not. Usually what you're seeing is live. You know, it's more exciting that way. So I've got my paper clip, and I'm going to hold it with the paper towel. Okay, that's the idea of this. I'm going to hold it with the paper towel, and I'm going to lower it in, and I'm hoping that the surface tension the surface tension, that's supposed to go down, paper towel, go down. Leave the, whoa, whoa, I did it. The paper clip is being pushed up by surface tension. And so now what I'm going to do is I'm going to bring my north pole to the end where it was stroking, and we're going to see what happened. Whoa! Oh! Whoa! Look at that. I'm actually, I'll be honest here, I'm pretty confused. I'll tell you why I'm confused. Look, I've got a little power boat. Boom, 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 boom. Woo! Ow! Woo! Just did it like a donut. Here we go. Ow! I have never made a little boat like this. This is a lot of fun. But as you can see, I can drag it with the South Pole. Woo! Or I can get the North Pole and push it away. Look at that. Shoom! That means I can push it away with the South Pole as well. I can too. So we know that the reason that we know that that one is magnetized is because if I get another paper clip, I'm going to attempt to float this one as well. What are the chances, do you think? Low. This is a non-magnetized one. There we go. When I bring my magnet in, it attracts it with that side and attracts it with the other side. So basically it doesn't matter which pole I bring the magnet to, or which pole of the magnet I bring to the paperclip, it attracts it. It's always attracting. Whereas this one here, attract, turn the magnet around, repel. That is the indication that this one is definitely magnetized. Oh, I can make it do wheel spins. But I'll tell you why I'm confused. I'm confused because I always learnt, and the textbooks always told me, that, yeah, that's definitely, I was always taught that when you stroke it this way, that this side becomes a North Pole. I'm sure that's what the textbooks say. And I just believed it, but it indicates to me that this might not be true. So I'm going to do one more try. This is definitely the north. This is the long side of the paperclip that I'm magnetizing. So I've always thought, since I was a little boy, 5 years old, that I would be making this a North Pole. But now I've got a suspicion that my life is a lie and I've been wrong this whole time. Okay, that will be long enough. And let's pop that into the water using my harness. My strap. Sort of got to balance it a bit. Okay, in you go. That's it. Now, my hypothesis is that that side is north. Therefore, if I bring in the North Pole, it should repel and it attracts. I've got to double check the textbook, that's for sure. Anyway, there we go. How does one destroy a magnet? Well, You know how you have all the domains lined up in the one way? You have to cause them to lose their direction. And you can do that by smashing them over and over and over with a hammer. That will actually do it. Or, and you've got to be careful here, by heating it up red hot with a gas torch. That, as it gets red hot, they'll slowly move and change directions. Anyway, that was a very interesting lesson for me. And I'm going to have to go and check the textbooks. Maybe Jacob's made this big discovery that all the textbooks are wrong. We'll find out. More than likely, I'm the one who's wrong. But anyway, off we go. Anyway, hopefully you've enjoyed this lesson. I look forward to seeing you again soon. Bye for now. Bye. Hey everyone, welcome to lesson 22, the strength of different magnets in the Year 8 High School Physics course. So, this lesson is about setting up an experiment for you to do yourself. We've done a lot of experiments in this course, and so I'll outline it and then you can go ahead and do it. You can write down the aim, your hypothesis, your method. You can do a results table, do the experiment, record your results, graph the results, discuss trends, discuss improvements, discuss, any future research that should be done, and then you can have a conclusion which goes and answers the aim. And so what is the aim? The aim is to compare the strength of the three magnets found in the physics set. So the three types of magnets we've got a bar magnet, and in this little vial there's 5, they're not large, but there's 5 very small cylindrical magnets, neodymium, and 5 larger cylindrical neodymium magnets. And we want to compare the strength of all three. Now, how do you do that with the equipment that you've got? Well, I suggest that you need a book. Now, why do you need a book? Because a book has got pages. Okay, a book has got pages. And if I take a bar magnet and I put it under page number 1, right, and I get a paper clip. Now, what might be the best way to set this up? Maybe not a book that you love. What have I got here? The Low GI diet. Yeah, well, maybe I need to go on that diet. I don't know. 1 page. Oh, look at that. The magnetic field definitely goes through 1 page. Right, will it go through 2 pages? Oh yeah, it goes through 2 pages. Will it go through 3 pages? Find out how many pages the magnetic field will go through to affect the paperclip. Then you can do it for the other 2 different magnets, and that would be a good way to determine the magnetic penetration through the paper, which I think would indicate the strength of the magnetic field. So very, very short lesson from me, but quite a interesting and not overly difficult, but you can work through it and come up with some results, some conclusions. I mean, I'm pretty sure that large supermagnet is going to be a lot stronger than that one. That's what I think. Is it a fair experiment? I mean, really, the answer is yes, but I mean, if you had as much neodymium here as the size of the bar magnet, well, then it would be a really, really strong magnet, wouldn't it? That would be quite interesting as well. Anyway, well, I do want to say thank you for joining me in this course. I hope that it's been a worthwhile experience for you. I hope you've really done the hard yards, basically. There's been a lot of work, but the course has really been about learning to start to think scientifically, how to carry out fair experiments, which is ever so important for future scientific work. I've enjoyed teaching this course, doing these lessons. It's been quite tiring, but anyway, here we are. And I'm hoping that you'll enjoy it, that you've enjoyed it, that you'll tell others about it, and that in time to come you'll do the next course, the next science course with me. Anyway, over and out for now, and I look forward to seeing you again sometime. Congratulations, and goodbye everybody. See you soon. Over and out. I'm gone. Bye-bye. All the best. Good luck to your families, and see you later. Bye for now. Bye-bye, bye-bye.